Dear participants, a very good morning, you all, and I welcome you all on this fourth day of this online HTC entitled as Hybrid Manufacturing Processes, Opportunities and Challenges. So it's a very great pleasure and honor to have Professor Ramesh Singh from University of Malaya, Malaysia. So he will deliver his talk today. And before requesting him to deliver the talk, I would like to share some brief about him. Professor Ramesh Singh is an outstanding scholar and a fellow of Academy of Sciences, Malaysia. He has contributed significantly to the development and enhancement in engineering, science and technology in Malaysia, particularly in the field of engineering, education and ceramic engineering. He has served in various positions as Program Coordinator, Director of Research, Chair of Department of Manufacturing Engineering, Chair of Mechanical Engineering Department, University Senate Member, Deputy Dean Development, Deputy Dean Research, Director of Engineering Business Unit of the Faculty of Engineering, University of Malaya. In 2016, January, he was promoted to a senior professor, thus making him one of the youngest academicians in the country to receive such a accolade from a premier public research university due to his outstanding service and contribution to the fraternity. Professor Ramesh received his PhD from the University of Sunderland, UK in 1997 with a specialization in advanced ceramics for mechanical applications. He has made over 350 scientific publications, including nearly 240 peer-reviewed research papers. He has about 6,500 citations into his account. He has filed numerous patents for his inventions and received many accolades as a distinguished scholar. He has secured more than 15 million ringgit of research grants and completed the supervision of 74 postgraduate students, including 31 PhDs and 43 masters, all by research modes. He was the recipient of the prestigious IEM Young Engineer Award and won more than 75 awards both at international and national exhibitions on his research and innovations. He was recognized as the top 12 Malaysia Engineer Stars by the Institution of Engineers Malaysia in 2011. He was the recipient of the prestigious Science and Technology Award 2014, which was awarded by the Malaysia Torre Science Foundation (MTSF) in recognition of for his outstanding research achievement in Malaysia. He is also a fellow of five prominent professional societies: the Institution of Mechanical Engineering UK, the Institution of Engineers Australia, Institution of Engineers Malaysia, Institute of Materials Malaysia, and Malaysia Scientific Association. He is on the International Editorial Board of Ceramic International Journal, editorial board member of Advances in Material Research, editor-in-chief of International Journal of Mechanical and Material Engineering, and list is so long. So it's of a great pleasure, and because of the time constant, I need to stop over here because the achievement and the records of Professor Singh is so long, and the list is very large. So I need to stop over here, and I would like to invite Professor Singh to share his research experiences and enlighten our participant with his research conducted. Sir, please, we welcome you, sir. Please. Sir, please unmute, sir. Please unmute, sir.
Right, thank you, Dr. Ravi, for the introduction, and welcome everyone to this talk series. Foremost, I'm happy to be here. I thank the NIT organizing team for inviting me. I will basically give a short presentation about the University of Malaya, where I'm working. And then after that, we'll go into the proper presentation. Okay, let me just share my my screen.
Yeah.
Can you see the presentation, Ravi?
Let me check. Yeah, let me check, sir, please. Yes, sir, it is visible, sir.
Okay.
Yes, sure. It is completely fine, sir.
So you guys can see the screen?
Participant can respond, please.
Ravi sir, please ping the screen of Professor Ravi sir.
The screen is visible, sir.
You can see?
Yes, sir.
Yes, sir, it is visible.
Okay.
Yes, sir. Yes, sir.
All right. So basically, my title of my talk is microwave processing of engineering ceramics. Actually, there are a lot of topics that I can talk about, but I thought maybe for this to fit in your team, I thought that I talk something about processing. Okay. All right. I think Dr. Ravi has presented biography of myself. So I didn't expect Ravi to make that presentation. So my CV is almost a thesis. It's about 100-page long. But this is just a brief biography about myself. Okay, so as mentioned by Ravi, I graduated with a first class honors in mechanical engineering. And subsequently, I went on to complete the PhD in less than 3 years in 1997. So I finished the degree in 1994 and then subsequently the PhD in 97, all in the UK. I don't have a master's. Okay, in the UK, if you have a first class, you can directly do your PhD. Okay, I have 25 years of consulting, research, and tertiary education experience. I've been in many capacity as administrator, as a researcher, as a teacher, as a lecturer. My current position is senior professor of mechanical and materials engineering. I'm with the Faculty of Engineering, University of Malaya in Malaysia. I'm sure some of you all are familiar with the university. Currently, I'm actually on secondment to University Technology Brunei on a special request by the Brunei government. So I'm serving here as a senior professor for a period of 3 years. So I joined them in January 2020, and I'll be here until 2022, and then after that, I'll go back to University of Malaya. My background is actually on mechanical engineering, but I've served in multiple positions. One of my passion is on engineering education. So I've served while I was a professor in University of Malaya as an associate director for the accreditation department of the country for 2 terms, where I look at the accreditation requirement, policies, and stuff like that. I got over 350 scientific publication, 75 postgraduate student completed. I'm also a consultant professor with a Chinese university and several other universities as visiting professors. I have more than 85 awards. I'm quite active in research. So bulk of these are research awards for my invention. It's not only me that who gets the award, it's the team. I have a good team of students and colleagues. And this has given that opportunity to do a lot of research. To date, I've secured about $5 million US dollars funding for research. And I fellow for many organizations, as mentioned by Ravi. I think the main one is the Fellow of Academy of Sciences Malaysia. This is basically an honor to get into this academy, because only top scientists in the country are admitted as a fellow. Okay, so I got in at you can say a pretty young age. So that says volume of my work and my achievement in the country. I'm also a professional engineer chartered with UK body and also with Australia. And my research interest spans into many areas. Main thing, of course, specialty ceramics. I develop ceramics for mechanical as well as biomedical application. I always push the boundary. My main goal is to always use green material, low cost, and also friendly to the environment. That has always been my priority when I basically develop new materials for application. Okay, so my current interest is in laser welding. So I do a lot of laser welding with my counterpart, my colleagues in China. We don't have good equipment, laser welding equipment in Malaysia. But in China, they have a lot of high-tech laser equipment. So I have a lot of projects on laser welding. I do failure analysis as well. I do consultancy work on failure of engineering components. And this has widened my knowledge in terms of failure mode, corrosion, degradation of materials, and so on. And of course, in engineering education, that's my other passion. Okay, so I spend a lot of time in looking at how best to deliver engineering curriculum, looking at policies and stuff like that. Okay, so pretty much that's my brief biodata. Okay, a little bit about University of Malaya. I think it's not fair if I don't talk about my university. It's a very old university. It's 115 years old. Started in 1905 in Singapore. It started as a medical college, King's Edward VII College of Medicine in Singapore in 1905. And as it moves from 1905 to about 1949, in 1928, at that time it was Malaya. They formed Raffles College, and in 1949, the King Edward's Medical and Raffles College combined, and it is called University of Malaya, Singapore. Okay, so at that time, Singapore is part of Malaysia. All right, and at that time it is called Malaya, and that's where University of Malaya. It's the first Malaysian university. And after independence in 1956, and as time progresses, Singapore wanted to form their own government, and so the British allows that to happen. And in 1962. When after independence in 1956, 56, 57, and subsequently in 62, it was decided to have two universities. So basically, we retain University of Malaya, so we call it University of Malaya Kuala Lumpur, and NUS is what we know today, National University of Singapore. At that time, it's called University of Singapore. All right. So basically, NUS and University of Malaya, we are brothers and sisters. Right, and so both universities are basically 115 years old. Okay, so we have a long history. We are a comprehensive university. We cover all fields, as you can imagine. We have 13 faculties. We have 2 academics. These are languages, basically. We have centers, 3 institutes. These are language as well. We have, in terms of research, research have come very long way in University of Malaya. So now we have 4 main research clusters. So we try to group all our research in each clusters. We have a lot of research centers, more than 50. University of Malaya also have 1 private university. This is in a joint venture with University of Wales in the UK. And we also have one continuing education center. So this is a private arm that looks at running executive programs. Now, in terms of students, undergraduate, this is as of December 2019, end of this early this year. We have about 15,000 undergraduate students, 11,000 postgraduate students, total student about 27,000. Okay, so it's a big university. We have over 200 academic programs. Okay. Right, in terms of staffing, total staff we have about 6,000. Out of the 6,000, we have about 2,400 academic staff. These are professional staff. They involve in teaching and research. And then we have professional staff. These are mainly for managers, management, and so on. Supporting staff are technicians, office staff. We have about 2,900 support staff. So in total, 6,000. I must also mention that this is a government-funded university. So our main source of funding is from the government. All right, and we have, out of the academic staff, we have about 10%. 10% of our academic staff, they are international staff and they come from 40 countries. So we have the different people from different countries joining the university. This is basically why we maintain 10% is because of ranking. In the QS ranking, if you know the criteria, one of the milestone that they actually look at is the international content, and we need to keep about 10%. All right, so you can say about 10%, 240, 250 academic staff, they are international. Okay, we go for all kinds of ranking, as you can see all the numbers here. But I think what I want to highlight here is the World University Ranking. In 2019, last year, we were ranked 70 in the world. The recent QS ranking, we are ranked 59 out of 5,500 universities. Okay, so this is a real great achievement. But the journey to attain rank 59 in the world is not a straightforward journey. So basically, we have to really beef up on not just research, but academic excellence, employability of our graduates, and so on. So there's a lot of things that we need to put in place. Okay, not just looking at research per se. So academic excellence are very important as well. And where our graduates go and work, are they employable? So all these counts towards the ranking. So the university put a lot of effort in all this, okay, to ensure that we continue to climb the rank. As of 2019, these are some highlights. I just want to touch a little bit. If we look in terms of grant, this is in Ringgit Malaysia, but roughly conversion USD $1 is about 4 Ringgit. So if we look at total grant that we have received in 2019, from public 127 million, that's about 31 million US dollars. From industry, we receive about 5 to 6 million US. International grants, about 14 million US. So total, we are looking at 2019 itself, we received something like 50 million US. Okay, so from inside public industry as well as international. In terms of publication, we push the limit. I mean, all our academic staff will have to publish. We pay a lot of attention to the Web of Science, or we call it ISI index journals. As you can see, for 2018 itself, for Scopus listed, that's including conferences and other journals that are not ranked under the Web of Science. We have about 2,400 over articles for Scopus, and ISI about 2,400. Okay, in 2019, again, you can see we are way above 2,000 over article, and 60%, as you can see here, 60% of our article in ISI or Web of Science, they are Q1 and Q2. All right, so we put a lot of emphasis on the quality, and that's why we emphasize on the ISI. each one of us, depending on our rank, we all have our KPI, our key performance index. Yearly, we are assessed against specific sets of criteria. For my level, I need to maintain at least 6 ISI paper a year, 4 PhD students a year. I mean, that's basically a certain amount of funding that I must attract every year. So there's a lot of pressure being put on our academic staff as they climb the rank. Okay, so of course we receive a lot of support from the university. We also get projects through collaboration with our counterparts, in China, in other countries as well, in Qatar, and so on. Okay, and the rest is just supporting details, international grants, citations, and so on and so forth. And we also have strong industry links. That's very important. In the Faculty of Engineering, especially, I'm not presenting here on the Faculty of Engineering. When I was the Deputy Dean for Research, we attracted a lot of industry. We also set up the industry park, just like what MIT has done. They have an industry hub. In Singapore also, they have the same thing in the university, so industry within the university. So we have set up this industry park in the Faculty of Engineering, and we attracted about 300 million ringgit of funding from various industry. They pledge support to the park over the 5 years period. So it may not be in the form of money, cash in that sense. It can be in the form of equipment and sponsorship for students and so on and so forth. Okay, so this is the first faculty in University of Malaya to actually establish this industry collaboration, and we asked the industry to set up their research hub within the university. So we provide space, we provide the manpower and the knowledge, and they provide the funding and equipment and so on. So it's a win-win joint partnership. Okay, I've put this up just to show where we are in terms of our citation impact. This is taken from Clarivate, from Civil Data. It's a bit outdated. It's in 2017. I didn't have the time to take the latest one, but I'm sure there's a little bit more improvement from what I'm presenting here. But at that time in 2017, as you can see, the orange line represents the average for Malaysia, how Malaysia is performing in terms of 5 main areas: medicine, engineering, biochemistry. This one here is, let me see what is down here. Computer science, computer science and physics. Okay. And the other lines, the red, green, light blue, these are other research university. We have 5 research university in Malaysia. University Malaya, University Kebangsaan Malaysia, University Putra, University Science, and University Technology Malaysia. So there are 5 research university. These are research intensive university. Of course, University Malaya is the oldest. As you can see, what I want to really highlight is the blue line, the dark blue line here. As you can see, we basically way above the average how the country is performing in all these main key areas. And of course, most importantly, is in engineering. We are way ahead. Okay, so you can say that we are in the forefront. Okay, forefront in terms of engineering. Okay, the other one that I want to show in terms of impact per journal. So these are the 18 main areas where people normally publish. So again, the world average is given by this green line. The orange line is Malaysia. The blue one, the dark blue, is University Malaya. And you can see that is higher than world average in 18 out of 27 categories. And again, you can see in the area of engineering, we are really strong. Okay, chemical engineering, energy, engineering sciences, materials, yeah. So these are very much engineering intensive. Okay. All right, so I can go on talking about but this presentation is not just about University Malaya, but that pretty much give you a little bit about the background of all of you all are most welcome to visit the university if you are in Malaysia. So as mentioned, we are comprehensive. We always look forward for collaboration with anyone who interested to collaborate. You can go through the website. I've given a website here. You can check out the website and see. I'm sure most of y'all comes from different backgrounds and faculties, so you may have an interest to collaborate. You can always get in touch with me, or you can contact directly the faculty. Okay, let's go into the proper talk that I want to discuss today. I know not all of y'all may be in the area of ceramics and bioceramics, so I'll try to make it brief. There's not much of theory here, so it's not a presentation. I mean, it's not a PhD YWA where we need to talk about theory and so on. Basically, I'll talk very general about the area, so that you guys have appreciation of this technology, okay, how we actually process ceramics, okay. All of us think, when we think about ceramics, we look at if we go to our kitchen, you look at the cups, the plates, they are all ceramics material. Of course, in the toilet, a lot of ceramics are used, the toilet bowl, the sink, they are all made of mainly traditional ceramics. The ceramics that I'm referring to in my presentation, they are not clay-based, basically. They are basically advanced material. These are engineered. These are engineered material, and they are used for advanced application. All right, the one that we see, the everyday use like mugs and stuff like that, they are traditional ceramics. They probably are porcelain, okay, clay-based or porcelain-based material. But I'm not going to talk about porcelain today. We're going to look at ceramics as a biomaterial. All right, so not all ceramics can be used as a biomaterial, mainly because the material that we use in our body, it has to be biocompatible. Very important. Whatever we put in our body, it should not react with our immune system. All right, it should be there to support. Okay, so not all ceramics can be used. All right, but there are specific ceramics that can be used in the body. So basically, when we say ceramic we term bioceramic, these are ceramics material that are specifically developed to be put into our body. Okay. Now, these are some examples of useful bioceramics. There are a couple more than what I've shown here, but these are pretty much the gold standard, or the famous one being used worldwide. We have TZP, tetraconyl zirconia, polycrystal, we have alumina, we have bioglasses. These are basically sodium, calcium, phosphate-based material. And then, of course, we have the famous hydroxyapatite. These are calcium phosphate, and we have tricalcium phosphate. These are the chemical formula. No worries about this. Now, what is important is to look at the biological response of this particular material. The first category, zirconia and alumina, they are considered bioinert. Okay, so I have the definition here. Bioinert means they are completely inert and do not react. They do not react with the host. Do not react with the host tissue. All right. So what it means is that when we implant this material into the body, it will remain there as a foreign body. At the same time, it does not react with the hard tissues or the soft tissues in the body. So there will be no reaction at all. So the material is put mainly for providing the mechanical support. Okay. Then we have bioactive, as you can see here, for bioglass and hydroxyapatite. They are known as bioactive. What bioactive simply means is that this material can stimulate healing. Okay. And it actually tricks our body to think that it is part of the body because it has calcium and it has phosphate. Okay, and our body, our heart tissue, our bones are mainly calcium and phosphate. So when we put in, especially hydroxyapatite, it is purely calcium phosphate. It has the same chemical structure as our bone. And therefore, the body thinks that it is part of the body. And it actually stimulates healing. Healing means that there will be tissues ingression into the material if it's a porous material. So you have ingression of the materials, the capillary, the blood vessels, and so on. It will actually go in and integrate with the material. So it's called bioactive. All right. And then, of course, we have tricalcium phosphate. This is biodegradable, meaning that it does not stay permanent in the body. It degrades over time. Okay, it's called TCP or tricalcium phosphate. The whole idea of tricalcium phosphate, normally we use this as scaffolding in order to allow bone to heal, while this scaffold provide the mechanical support. And when the bone is healing, this tricalcium phosphate will be absorbed by the body. Okay, so it just breaks down into calcium and phosphate and it get absorbed by the bloodstream. All right. So this is called biodegradable and it's resorbable over time. In fact, researchers have also worked on tricalcium phosphate where they are able to control the time of degradation. So you can actually allow healing to take place slowly, okay, progressively, while the material gets absorbed little by little over time. All right. So these people have also worked on that in order to allow healing to take place. My current project with the medical faculty in University of Malaya, we are actually trying to develop a phosphate glue material for the open heart surgery. Okay, so current gold standard is that when they actually do open heart surgery, when people get heart attack and so on, or they have a blockage in the heart, so they have to do open heart surgery, and for that, once they cut open the rib cage, it's permanent. You will never get the rib cage joining back again, and they use a stainless steel wire in order to hold the cage together, and they just close it up, and so you will always have the stainless steel wire holding the rib cage together, and so there is a move to look at, instead of using stainless steel, we want to explore if we could develop phosphate-based glue. Okay, so whereby this glue, they are phosphate-based, so meaning that they are bioactive in that sense. They are not biodegradable, but they are bioactive because they have to remain there to glue the cage together. And at the same time, it has to harden, not immediately. It has to harden over a period of 24 hours to 48 hours. Because every time after a heart surgery is performed, the heart surgeons will have to stand by and monitor the patient. If there is any complication, reoccurring of blockage, they will immediately have to go in again to look at the condition and perform surgery. So imagine if it's hardened, then they have to cut it again, and that is going to cause a lot of trauma and discomfort to the patient. So having that time set in, it's the complex part. The bioactive part is not the issue, but having it to harden slowly, fully within 48 hours, it's a big challenge. So we are trying to integrate with some polymeric material and so on. So that's basically ongoing. Okay, these are just the anatomy of human skeleton, the body. I just want to show you where typically we have biomaterials or bioceramics being used. So for the skull, cranial, we call it cranial repair. When people have an accident or if you have a cancer, for example, in the skull, in the brain, and they have to cut open your cranial, this is the hard material that protects the soft brain from injury. So once there's a hole being made, it becomes a permanent feature. You cannot close that. And what the norm they normally do is they put a metal plate over it. Okay, so there's a move where bioceramics can also used in order to seal the hole. So cranial repair. Maxillofacial reconstruction, this mostly for people involved in motorbike accidents, they lose the cheekbone and so on. So, as we grow older, healing of our bone takes a long time. In fact, I think if you are at my age or maybe at your age, you guys are much younger than me, healing probably will be almost impossible. All right, if you want the bone to grow back, I don't think that will take place. So only way is to substitute or fill in the gap. So we use maxillofacial reconstruction. So we can use ceramics. Now with 3D printing, that's has really facilitated the use of more use of ceramics for maxillofacial reconstruction, because with 3D printing, we can basically take the image, X-ray image of the face or any part that we want to reconstruct, and then we can make the bioceramic to take the shape. So that has really facilitated the use of bioceramics in orthopedic application, this 3D printing. Okay, then of course dental. This one is a big thing, I saw just now while we were waiting for the presentation, many of you are still young. Young means maybe in the 30s or 35, still in the 3 series, you better take care of your dental. That's very important. I had almost all of my main molar has been root canal, and I lost one big tooth last year. And it's, you cannot replace it. You want it to grow back, it will not happen. Only way is to put in implant. And believe me, it's not going to be comfortable, to have an implant. We will see more on this implant later so that you will understand. Okay, I have a video at the end to show you on the typical ceramic implant, how the procedure and so on. So maybe, hopefully, that will make you to think, that dental is taking care of our tooth, very important. Okay, anyway, heart valve, artificial heart valve, there are research where ceramics are used as valve. One of the good thing about it is that if it densifies fairly high, it is very smooth, and so in order to get clogging, it's difficult when you have a smooth surface, so we have used that, people have used that as artificial heart valve. And of course, a lot of work being done, especially in Europe, on load-bearing application for orthopedic, where in the Europe, in the US, we have very high percentage of people who are obese, heavy in that sense, and as they grow older, they suffer fracture at their pelvic area. And therefore, in order to give them mobility back, they have to put in this prosthetic, this metal piece inside that goes into the femur and the pelvic area in order to give them that motion. Because if this part breaks, because this neck is, it's not very big, maybe about 15 to 20 mm in diameter only. And because it's a small sectional area, you can imagine the amount of load that it has to sustain, the body weight it has to sustain over a small area. So over time, as you grow older, our bone loses the calcium, and therefore it gets porous and breaks easily. All right. So a lot of work done in the Europe where they use artificial biomaterials, and ceramics are used basically to support the orthopedic, for the pelvic, the joint here. Okay, of course, the other one is the total knee replacement. This section, mainly polymeric materials are being used. And the other one is calcaneal repair at our feet. When we have a lot of, in Asia region, there's a lot of accidents and people actually break their bone in the feet area. So they call it calcaneal. In this calcaneal repair, you see that, you have bones fragmented, and therefore you will definitely need to hold the bone together to allow healing to take place over time. This picture just shows some of the biomedical application of materials, not just ceramics, can be metal, can be polymers as well. This is an X-ray showing how metallic bar, mainly stainless steel or titanium, are being put into the bone in order to hold it. There's a fracture here, if you can see. There's a fracture. So in order to allow healing, because as I mentioned, healing takes place very slowly. All right, so metallic implant are being used. You see, one of the main issue with ceramics is that it is brittle. It cannot sustain tensile loading, and therefore it cannot be used universally for all biomedical application. Areas where there are tensile loading imposed on the joint, ceramic would fail, and here we need the support of metal. Okay, so metal will do very well, but metal are bioinert. Okay, they are biocompatible, they are bioinert, they are not bioactive. So meaning that it will remain as a foreign body in the body. All right, it will be a foreign material in the body, and over time it may need resurgery to change the metal, maybe because of loosening and so on and so forth. And then I mentioned just now total hip replacement. As you can see this X-ray, you have your pelvic section. So this is where you have the metal piece, the stem. This stem, metallic stem, they can be made out of titanium or stainless steel, and basically they are basically put into the femur, and the other part goes into the pelvic area. All right, and the pelvic area is here where ceramic comes in play. We have the femoral head, which looks like a ball at the tip here, this part here. Most of the design that is available in the market, they have ceramic head, and these are made out of tetragonal zirconia. They use tetragonal zirconia because tetragonal zirconia, they are very durable in that sense. This section sustain mainly compressive loading. As you can see, the load is always compressing. The tensile loading is carried by the metal piece. All right, so the metal carries the tensile loading. So the head needs to be strong in compression. So ceramic works very well. And the other important aspect of ceramics is that it exhibits very low coefficient of friction when it comes into contact with polymeric lining, or we can use a ceramic lining as well. So we have a ceramic cup and we have a ceramic head. So we have a ceramic versus ceramic, so they can be made out of zirconia, both pieces, or we can have a ceramic with a polymeric, the cup. Right, and research have shown that the wear rate is very low. Right, so this is one of the advantages of using ceramic in that sense. And then, of course, I mentioned about TKR, the total knee replacement. So these are polymeric material. I think Asian people, most of Asian people do not suffer a lot of this knee replacement, but certainly in Europe, US, we have total hip replacement, we have total knee replacement, very common because of their weight. All right, as they grow older, they become heavier, and their legs won't be able to sustain the loading. And of course, dental. So we cannot run away from this. When you lose your tooth like here, it will not look nice that you have a gap in between. If you lose at the back, like I lose my molar right at the back, inside that's fine. I did not want to put a replacement. In fact, I thought about it, but because it's right at the back, I thought that I can live with it. No one will see that I don't have a molar right at the back there. But if you lose your tooth in between like this, then some people, they lose their self-esteem. When they lose their tooth like this. So only way forward is to put in an implant. So basically, you have an artificial implant that is basically put in. All right, and in the past, these are made out of metal, but today you can have an all ceramic. The stem, the implant itself, it's called a abutment. And we have the tooth itself. They are all made out of ceramics. Okay, so I'll touch a little bit on this as we go along the presentation. Okay, this is the cranial the repair. So, when you have an injury, you have the bone which is fragmented, as you can see, into several parts like this. Now, there's no way in the lifetime of this person that this bone is going to heal. All right. So the only way is to really put the metallic, the kind of like a strip in order to hold the bone together. All right. And we can only hope that over time, healing takes place. But once you have this in, walking will be very difficult. There's a lot of discomfort and so on and so forth. And we have a lot of the case like this in Malaysia as well, because, a lot of people ride motorbikes in the country. And because it's one of the cheapest transport mode, I think in India it's the same thing. And, when you get involved in accident, you cannot run away. If you are unlucky, you have you fracture here and your calcaneal bone are all broken up. And the only way is to use a biomaterial in order to hold them together and allow healing to take place. All right. Unfortunately, there's no super glue. We don't have a super glue that can glue this. So hopefully with the glue that we developed in order to use for the heart surgery, maybe this can also be extended for usage like this. Okay, microwave materials processing. Basically, when we look at how we process ceramics, or manufacture ceramic components, there are two ways, two categories basically we can classify them. One is by the conventional route that we know, thermal conduction through radiation, convection. In modern days now, we use laser heating as well, plasma, electric heating, infrared and UV heating. And then, of course, then we have the non-traditional way of doing things, that is induction, radio frequency heating, and microwave heating. All right. So this heating, RF and MW, short form for microwave, they are known dielectric heating. Okay, dielectric because it depends on material, dielectric properties. So it actually capitalizes on the ability of the material to couple microwave or radio frequency. All right, and they can vibrate on a molecular level. You have vibration of the atoms that creates heat, and thereafter, heating takes place or sintering takes place and so on. So why microwave? Okay, so I have microwave serves the scientific community. Okay, first thing is that it saves energy. All right. So if we look at this has been proven worldwide. There's a lot of papers published in terms of the benefit of microwave. Okay, if we look at this data is from Japan. If we compare microwave versus conventional heating. Okay, and if you look at the amount of time taken, all right, microwave, in order to achieve whatever you want to do with the production, microwave consume 20 hours of production time as comparison to 96. This is for sintering of alumina, sorry. This is when we want to sinter alumina. Of course, this time will differ depending on the material that we are processing. In terms of energy consumption, of course, if we use less hours, less consumption, in comparison ratio between microwave and conventional. This conventional means is through induction heating, normal heating, using electrical heaters. As you can see, 110. So microwave consume 110 of the energy. In terms of processing time, 1/5 of the time taken by conventional. Okay, conventional means. And in terms of energy, obviously, this is in US dollars. Whatever the country, wherever you are, when you actually take the amount of energy per kilowatt hour and you times the the rates, it's going to be cheaper if you consume lower energy. So it's in this case, it is 1/6. Okay, 1/6 of the overall cost if you compare to conventional. All right, so it saves energy. It's effective and rapid. Okay, it's a very quick process. If you look at the profile here, this is basically for in my work when we actually compare effect of microwave versus conventional heating in a normal furnace for hydroxyapatite. Okay, for hydroxyapatite. In order to reach the same temperature. So remember earlier I said that it depends on dielectric properties of the material. So using the same material, but you heat it in a different mode, microwave mode versus conventional, as you can see, very rapid. Very rapid. It reached to whatever temperature you want as compared to conventional. So conventional heating may take typically up to 600 minutes. This you talk about a fraction of 30 minutes or less. All right, you go up straight to whatever temperature you want, hold it for maybe 5-10 minutes or whatever time that you desire, and then after that, shut off the power. Once you shut off the power, the cooling takes place in the furnace, and within half an hour, your material is ready for use. Okay. All right, so it's effective, it's safe energy, it's effective, it's rapid, it's versatile as well. All right, so if we look at history, a little bit of history, microwave started a long time ago before you and I were born, in 1940 as communication. And then in the 50s, 60s, they extend the usage, not just for communication purpose anymore, they use for rubber curing, vulcanization, and then slowly in the 60s, they start using it for food processing because they find that water couple microwave very easily and it heats up very rapid. So it can be used for cooking. So that's how microwave came into our kitchen. Okay. It able to use for tempering, pasteurization, roasting, where we want it to be consistent, because one of the beauty about microwave is that because it depends heavily on the dielectric property of a material, and most material, they are quite homogeneous in that sense, so you can get constant homogeneous heating, okay, and it's instant. Right, rather than the conventional mode of heating. All right, and then drying was the main industry that actually utilized microwave for drying purposes, because drying are low temperature application, and in order to ensure consistency in products, and when drying is concerned, we want to have consistent in terms of drying. So microwave works very well. Okay, and of course in the textile industry as well. Okay, and then in the 60s to the 70s, they realized that microwave can actually increase temperature slightly higher than 100 degrees C. And so we have low temperature application, and that's where we start to use it into biochemistry, into chemistry, for petroleum, for medical usage, and so on and so forth. And when I was born in 1970, they started using microwave for high temperature application. Okay, so that's when ceramic processing started. The pioneer people, they started microwave is in the US, Professor Roy and Professor Agrawal. I know Professor Agrawal, I worked closely with him in Penn State. So they were one of the pioneers that started microwave sintering of ceramics. Okay, so that's when in that span of 10 years, a lot of work has been focused on ceramic processing. Okay, they use it at synthesis level, they look at joining, they look at sintering, consolidating the material itself to make it hard. Plasma synthesis. Just now I mentioned about, ceramic, they are weak in tensile, but strong in compression. And so basically, one way to complement the weakness of ceramic in tensile is to apply coating material. So ceramic has been used as coating onto a metallic implant. And this has given the opportunity or the ability of the implant to have an outer layer, which is basically a you have a bio-inert and a bioactive coating. All right, so the bioactive coating will cause some very good reaction with the host tissue. You have good bonding, while the stem will give you the bio-inert. Okay, so coating, people start to develop and see how coating can be used through microwave method, and of course sintering. And thereafter, there's no stopping. In the 1900s, people look at various ceramics, difficult ceramics, where we cannot sinter We need very high temperature like non-oxide ceramics, like tungsten carbide, cobalt. They typically need very high temperature in order to sinter silicon carbides and so on and so forth. In the 2000, the microwave has also been applied to metallic materials, and that's when brazing and joining and welding starts to kick in. All right, so people now use hybrid heating, combining plasma and microwave, or conventional and microwave, or brazing with microwave and so on. So there's a lot of work being done in hybrid heating, okay, using conventional versus microwave. All right, so these are some new application. I mentioned this already, microwave, the hybrid heating. All right, so these are the new areas where people are basically focusing in. All right, so this basically shows the versatility of microwave energy. And of course, it's economic. I think we have seen an example of this. Now, this is another data from Canada, as you can see. The savings, these are all ceramic material. If we take, for example, brick and tile, there are two sections here. One is drying, the drying section, comparing conventional drying in terms of amount of power being used, okay, per hour versus microwave. As you can see, very, very low, almost more than 50-60% lower than conventional, okay, the power usage. All right, 16.63, 8.3. Likewise for firing, when once you get a green body, you need to fire them, to consolidate, make it hard. As you can see that for bricks or tiles, it consumes about 200 kilowatt times 10 power 6 kilowatt hour per year, in comparison to firing, which is way, way low, almost 10 times lower, as you can see. And likewise for other electrical porcelain, glazes, advanced ceramics, compared to 4.6 to 0.46. So basically, in terms of comparing microwave versus conventional, whether it's drying and heating, there's a huge saving. All right, and I just take the cost in Malaysia is current electric tariff for commercial is about 38 cents per kilowatt hour. That's what the current tariff is. Now, if I use this as the guide, and if I times against the power usage, the savings is in ringgit, but I convert to US dollars, 1 to 4, talking about 19 million US dollar saving just to process bricks and tile. And porcelain, electrical porcelain, 1 over million, glaze, 5 million. So these are big industry, okay, in the ceramic industry. Sanitary wares, okay, in sanitary, they developed the porcelain bowl, and then after that, in order to impart good surface finish, we normally put a layer of glass on top of the surface, and then after that, we need to consolidate that glass so that it becomes smooth. It closes up all the porosity on the surface, and we can selectively heat, use microwave, selectively heat. We don't want to heat the whole body. We just want to heat a thin layer of the surface and the glaze so that there's fusion and you have the glaze formation. So microwave allows all this to take place. So it's quite economy. I mentioned about selective heating. I just want to show you this diagram. There's many more examples. Imagine you have a system, and in the system, you have many things, and you only want a certain part to heat up at a certain time, and you don't want the whole section to heat up. Now, microwave can be used in that sense. We can selectively heat sections or areas that we want heating to take place. All right. So in this example, you can see that this is the production of hydrogen. In this example, a catalyst, basically activated carbon, combined with palladium are being used. Now, this activated, actually palladium is the main catalyst, but activated carbon is being used because carbon has very low dielectric loss, high dielectric loss. So it couples microwave very fast because of the carbon, right? And when it couples microwave very fast, it heats up rapidly. And so we have the surrounding can be maintained at a particular temperature, but you can have particles that like in this case, the catalyst, activated carbon, which heat up very rapidly because it couples microwave as microwave pass through the medium. The medium will not react or will not couple microwave, but the activated carbon will couple microwave and it starts heating up very rapidly. And you can see the temperature can go up to about 550 in comparison to the surrounding. And therefore, you have localized heating and the production of hydrogen can be rapid in comparison to conventional heating. Conventional heating, you need to heat up the medium. Then heat is transferred from the medium into the catalyst. So generally, you can see the temperature of the catalyst will never, the most it will go is similar temperature as the surrounding, or it will be lower because it takes time to heat up. All right. So there is a considerable saving, shorter time for hydrogen evolution in a much shorter time because of high temperature. A lot of saving in this article. The author actually highlighted 76% saving in terms of energy. And as you can see, the power usage, 33 watts versus 139 watts based on conventional heating. So there, again, it emphasized the basically the cost savings, energy savings, and selective heating, okay, with microwave. I mentioned about the mechanism, so just very quick. I don't want to discuss theory. When we look at the conventional versus microwave, as you can see, in the conventional we depend on heaters, and then the electric current heats up the heater, and then heat is transferred from through convection. First you have conduction, and then convection from the electric heaters onto the sample. And once it goes onto the sample, again, there will be a temperature gradient because not all material are good conductors of heat. So the surface may be very hot. As heat is transferred onto the inside, you have a temperature gradient in that sense, okay? In comparison to microwave, because microwave depends really on the dielectric properties of the material, so you have volumetric, we call it volumetric heating, meaning that at every point of this sample, that if we measure the temperature, it will be consistent. Because microwave pass through throughout, and every atom that able to couple microwave will couple and will start heating up. Okay, you have friction and therefore volumetric heating takes place. So you have uniform heating. You won't have temperature gradient. Okay. All right, so this basically tells you why microwave being preferred over conventional heating, all right, because of volumetric heating. So it's quick, fast, efficient, consume less energy, and basically for ceramic processing, it is very good because you have a uniform temperature gradient. You don't have thermal gradient develop in the structure, which can cause cracking of the material on cooling. All right, so it just, again, inside out, right? So the heating takes place from here, head outwards. Basically, it's throughout. And in the case of conventional, it gets hot first on the outside and then it moves inward. So there will be a gradient build up. Okay, these are some advantages of microwave. Okay, it saves time, saves a lot of energy, as you can see, volumetric heating. Very important for low temperature heating. That's why it's being used for drying, as you can imagine. We don't need to depend on putting it in an oven for a very long time because we know that there are volumetric heating. You have consistent heating throughout, inside out, rather than outside in, right? So very famous for drying. Okay, uniform heating. So if we want to get uniform heating, like in the drying process, we can use insulation and susceptors that are able to maintain a very good uniformity in terms of temperature, ability to achieve high temperature, even with our own household microwave. I've modified household microwave, and you can really reach temperature way above 1,500 degrees centigrade. You don't need to have a specific high power special furnace to do this. Even the household microwave able to achieve this. But the key thing is that the insulation, right? How we insulate. And of course, it also depends on the material that we want to process. The good thing is that if we able to maintain a short time in terms of heating, we are able to refine microstructure. You see, the key success to ceramic usage in industry always goes back to its microstructure. If we can keep the microstructure as fine as possible, then we are able to enhance mechanical properties. If you recall back your materials engineering days when you were a student, you recall the Hall patch relationship. So there is an inverse relationship between strength or mechanical properties for that matter versus grain size. The smaller the grain size, the better the mechanical properties. So it gives you better quality in that sense. And of course, finer microstructure, we can even get nanostructured material. Selective heating, I talk about. Because of selective heating, we can choose specific brazing material or interlayer that couple microwave at very low temperature than the base. So therefore, we can heat up the interlayer so that the interlayer becomes soft and cause bonding to take place at very low temperature without affecting the base material. And of course, it's eco-friendly. So it's better, faster, cheaper, and greener because it doesn't really pollute the environment. Okay, I'm just going to show a couple of slides on some materials that we have processed. If you are familiar with alumina, you know alumina is very difficult to sinter by conventional means. You need very long time, high temperature, way in excess of 1,500 degrees centigrade or 1,600. You need long sintering times. And most of the time, you ended up with undesirable grain growth. Okay. And when you see large grains, the properties are most of the time very low. All right, so microwave helps to minimize grain growth and enhance mechanical properties. So this diagram is taken from a paper in 2003. It's not my work, but these other researchers. But what I want to show is that we look at the temperature by conventional means. If you look at this line, this is 1350. At 1350 sintering of alumina, even after 1,000 minutes, okay, you look at 1,000 minutes, that's about 16 hours. 16 hours in a furnace. Okay, temperature, your density is only about 75%. All right. As temperature goes up, as you can see, the densification, the processing time can reduce. So there is a compromise with conventional heating. High temperature, you can reduce the residential time in the furnace. All right. So this one you can see 1600. Okay. Still, you need up to about to reach about 100 minutes at least to 200 minutes in order to get very high density above 95%. Okay, and temperature is very high as well. Now, on the contrary, if we look at microwave, all right, look at the temperature. I mean, 16, 15, 14, 13, 50. You have 1350, 1275, 1200, 1150. So low temperature, right? Now, when we consider, I just want to compare this line, the blue one, it's 1350 with this line, all right? This is 1350 as well. Now, if we compare this, we're at 1350 with conventional, even after 16 hours or 1,000 minutes, you only getting about 75% dense. In microwave, we talk about maybe a fraction of 10 minutes here. This is 50 minutes. In the fraction of, less than 10 minutes, you are already hitting 95% dense at 1350. All right, so that's really fast. All right, so these are one of the advantage of microwave heating, basically. But this just looking at microstructure at 1200. Conventional sinter, you can see it's porous. A lot of big holes here and there, and you don't get a proper consolidation. Typically, if you sinter alumina at 1200, your density is only about 47% dense. Okay, this is for 120 minutes. Now, maintaining the same temperature and the same holding time with microwave, as you can see, this fracture surface, 98% dense, almost fully dense. All right, so a lot of advantage with microwave. So this is another one that I've done with my student. This high temperature at 1500. As you can see, what is important to note is the grain size, right? Very large grain, elongated grains. This structure exhibit low properties. Grain size 2.37 micron in comparison to microwave at the same temperature. but at a much shorter holding time, achieve better densification, and look at the grain size. This is more than 50% smaller. Okay, and obviously there's a lot of improvement in the properties as well. Most of the time we see that microwave, when we use microwave for sintering, we are able to reduce the temperature in comparison to conventional by more than 200 degrees centigrade. And of course, time-wise, in a fraction of minutes, all right? We are talking about minutes, but in terms of temperature, 200 degrees lower. Yeah, some of y'all may say, oh, it's just 200 degrees. It may not have much effect in terms of the current and so on. So maybe you are right. But when we take into consideration the time spent, this would typically take 24 hours or more, okay, in order to reach whatever densification you require. For the same amount of temperature and effort, you will spend less time, less energy in order to reach even better properties. All right, so the benefits are definitely there. Okay, we also sintered zirconia using microwave. This is just a typical microstructure, but what I want to highlight is 2 minutes holding time. We sinter it for 2 minutes. We are getting about 97% dense, very fine microstructure. Okay, so this diagram basically shows the effect of microwave. We have undoped zirconia versus doped. We use copper oxide. I highlight copper oxide because part of my work is not just looking at processing. We also aid the processing through the use of low temperature or low melting additives. So I use copper oxide and manganese oxide most of the time because this transition metal oxide melt at very low temperature. So what I want to highlight really here is that, okay, if you look at this diagram, this is relative density. This is the dotted line. This is undoped. That means these are pure zirconia, which are sintered using the normal furnace, conventional sintering. So if you can see, the focus is always at low temperature. The high temperature, basically, of course, given time, whether it's microwave or conventional sintering, they can reach to whatever properties you want. But you know, as mentioned, the whole benefit of having microwave processing is really to focus at this region, the low temperature region. Okay, we want to achieve densification at low temperature. Why that is important, I think you know, because we are able to save energy. We are able to keep it cheap, okay, economical, all right, rather than going at very high temperature. Okay, so focus is here. Now, with undoped, as you can see, okay, right, 1300 only getting about 95%, okay. Now, when we use microwave, this darkened line, this is with microwave, so it went from 1100, if we see, it went to about 57% up to maybe about 78% dense. Okay, this is by microwave, so still not very good. So microwave is not the solution to our processing. We can enhance this by improving the material, because the key to microwave is really looking at how we can enhance the dielectric properties or the internal structure of the material. And we found that by doping small amount of copper oxide, okay, about 0.2%. Okay, this 0.2%, this one, and you can see that it really went from when we have copper oxide doping, this no doping, copper oxide doping, it went from here to here, about 70%. But when we couple copper oxide with microwave, it came to 95%. So this is where we actually benefited by combining the material aspect, where we modify the material aspect through addition of small dopants, in this case, transition metal and microwave, right? And all this achieved at 1100 degrees centigrade. And we use small amount of doping only, 0.2%. All right, so this you can see how copper oxide doping actually aided microwave, all right? This just to show microstructure development. As I said, my focus always has been on the low temperature processing. You know, still high porosity. Of course, when it comes up here through microwave, you see a better structure. The grain size about 0.12 micron. But with microwave, you get even finer. All right, less than 0.1 micron. I mean, it looks the same, but this is at higher magnification and much smaller grain size. All right. Okay, this further example on transparent. We can also make transparent material. This for optical purposes. So these are transparent alumina material doped with different transition metal. So these are chromium doped. So it's pink in reddish in color. Vanadium give you green, but they are alumina based. Why these dopants are being put? Just like in the case of I just shown earlier, copper oxide, it aids densification. All right, but so this one allows us to also process. If we process the alumina to be very fine, we are able to sinter it at very high temperature using microwave in order to get transparent. And these can be used for optical purposes. All right, these are aluminum oxide as well. We can also put in any pattern or fashion that we want in order to make it transparent. Okay, so this is shared by my counterpart, Prof. Agrawal from Penn State. Okay, this is spinel. This is hot press spinel combined. This is hybrid heating, aluminum nitride, as you can see, transparent. This is basically my work. My group work, hydroxyapatite, we are also able to make it transparent. Okay, at very low temperature, as you can see, 1100 sintering for 10 minutes only. This is another for growing carbon nanotube onto silica substrates. Very low temperature, 700 for 5 minutes. Okay. All right. Let's look at the two most famous bioceramics that I've been working on, hydroxyapatite and zirconia. As mentioned, hydroxyapatite, excellent biocompatible, we've seen earlier, due to its chemical similarity with the portion of our heart tissue, so because it has calcium and phosphorus. So this is a natural occurring structure of HA. It has calcium, it has phosphate, and basically it blends in very well with our host tissue, our bone. And of course, then tetragonal zirconia, I call it TZ short form. It is also known as ceramic steel. We will see in a while why. It's very strong, superior mechanical properties, and can be used for mechanical and clinical application, basically. Mentioned just now, it's bioactive. And tetragonal zirconia, they are bioinert. Okay, bioinert means it does not react with the tissue. Bioactive means it supports ingrowth of the tissue and so on. So these are the two different classes of ceramics that I work with. And as mentioned earlier, also I try to always look at using green processes. This couple of years back, we actually use eggshell as our calcium source. So we process chicken eggshell. We process it, we apply microwave, we apply also conventional, but we found that microwave method, chemical assisted, we call it chemical assisted microwave method. The process is much more homogeneous and it's rapid, and we are able to produce nano HA powders. Okay, so there is a process that we put in, but generally we use eggshell. We combine it with phosphoric acid, subject it to microwave heating, and we get nano HA powder. And this HA powder then can use for all sorts of application, whether as coating or solid implants and so on and so forth. Okay, so there are engineering processes that go into it, but generally it all requires fine tuning. Okay, fine tuning of temperature, the processes, and whatever we mix inside. This showing the X-ray diffraction of the powder produced by microwave versus the human tooth. This is basically my wisdom tooth that I extracted some 15 years ago. While the dentist was extracting out the tooth, I was just thinking I could use the tooth and do X-ray, and I can compare and see whether it's biocompatible. So this is the enamel, the hard part of the tooth. I've done the X-ray on this part, and the X-ray looks something like this. And this is the X-ray of the powder, and as you can see, quite similar in that sense. They not exactly match, but where the main peaks are occurring, you get the same thing on the HA powder. So basically it just shows the compatibility in that sense between natural occurring hard tissue with the synthetic material that we produce in the lab. This is another work that we did in order to show the biocompatibility nature of the material that we develop in the lab, the HA that is being microwaved. This I have to work with people from the medical faculty. This sample has been implanted in the tibia of a rabbit, basically, just doing a small incision and placing the small sample into the bone. And after about 6 months to 8 months, the rabbit is sacrificed. And when we looked at the cross-section of where the sample are being placed, we see very good bonding between the hydroxyapatite, the synthetic material, with the bone. So basically, the bone thinks that this is part of the bone. All right, we don't see any infection or any injury within the structure of the bone. All right, this is just showing the comparison. Generally they are quite compatible, the dense body that we produce versus the bone and the enamel. One thing that I want to highlight is if you look at the elastic modulus. Now, bone typically they are low. Okay, the elastic modulus vary between 10 to 22 depending which bone we are looking at. Enamel is slightly more stiffer, like our tooth. They are more harder in that sense, but bone is slightly flexible, so it's not high. But if we look at hydroxyapatite, because this material being densified, fine grain size, it's become very hard, and the elastic modulus can be very high, 35 to 120. Now, this is where we need to carefully process the material, because if we implant hydroxyapatite into the body and if it's fully dense in that sense, it has very high modulus, what will happen is that over time, the body will pass the load to the implant, and the natural heart tissue will not carry the load. So when the natural heart tissue don't sustain the load, you know what will happen? The bone, the heart tissue will degrade over time. Because our body requires, that's why we do exercise in order to strengthen the body so that the bone stays alive. Because this is a living cell. So if we put in a very strong material in it with very high elastic modulus, then the body will say, hey, you are stronger than me, why not you carry the load? And what happens over time, the bone loses its strength. All right, so this is something that we need to engineer the material to have some porosity so that the Young's modulus are not very high, okay, in that sense. Okay, this just again showing the effect of, conventional versus microwave. So we've seen this less than 30 minutes at different temperature, as you can see, very good. What I want to show here also, you see high temperature sintering, microwave give not much benefit. I mean, no much changes as we increase temperature. Anyway, that's not the purpose of why microwave is being used. The whole idea of microwave is really to focus at the low temperature end. Okay, so we need to understand that. This is just showing the time taken, to sinter at different temperature. I just show you at 1,000 degrees, takes about 1,000 minutes. If you're looking at 30 minutes, of course, slightly higher density, but it does not matter because, as mentioned, that anything above 90-95% dense, that's good enough. Small amount of porosity in our ceramic is good because it allows fixation, mechanical interlocking between the hard tissues and the surface. So we have some porosity, that's good. The hard tissues, the soft tissues can grow inside. Okay, just microstructure. What I want to show really, this is by microwave and this is by conventional. Look at the scale. Okay, we are talking about 10 micron versus 1 micron, 2.5 micron versus 1 micron, 5 micron versus 1 micron. All right, so I mean, that really tells you that we are talking about fine grain microstructure. This clearly shows you 10 micron. You can see this is at 1350. Both are sintered at 1350. This is a one-fifth of the grain size. All right, so you can imagine the properties on this are much better than this. Right? Fourfold increase mentioned in terms of grain size. Right, that's on HA. Right, let's look at zirconia, a little bit about zirconia. If you are familiar with this area, zirconia exists in three crystalline structure, monoclinic, tetragonal, cubic. So as we heat up, it goes from monoclinic to cubic. There is a volumetric shrinkage as it goes from monoclinic here. And on reverse, there are expansion. Okay, so one of the issue with ceramic is the reverse cooling. When it goes from cubic back to monoclinic, you have the disaster, you have cracking of the body. So in order to avoid cracking of the body, we normally don't use pure zirconia. We stabilize the zirconia using some other stabilizer, and normally we use either magnesium oxide, calcium oxide, or yttrium oxide. Most famous is yttrium oxide. Okay, this allows the stabilization of the tetragonal phase, okay, at room temperature. And this is a little bit of material science. I will not go into it. So we add in 2.53 mole percent yttrium oxide, and that able to stabilize or retain the tetragonal structure at room temperature. So if I go back to this diagram, we are able to retain this tetragonal structure, which normally exists only at about above 1100. Now we are able to retain this structure, which looks something like this at room temperature. All right. So yttrium oxide lowers the chemical free energy for the transformation, and therefore it avoids phase transformation. And subsequently, this material is known as yttria tetragonal zirconia polycrystal, or YTZP. I just call it TZ. Okay, for that sense, it's fully tetragonal. When it's fully tetragonal, it gives the strongest or the highest mechanical properties that this zirconia can have. And this is because of its self-healing ability. We call it transformation toughening. All right. So how strong is YTZP? This just to give you an appreciation in comparison to steel and cast iron. We look at tensile strength. We are able to engineer the material to have a very strength from 600 megapascal to 1300 megapascal, which is much higher than alloy and steel. If we look at the Young's modulus, 205, a fully dense tetragonal zirconia, exhibiting a characteristic, elastic characteristic of a metal. And that's why it is also known as ceramic steel, all right, because of its elastic modulus, all right, very resemble very close to steel. And of course, the toughness from 5 to 10. Of course, alloy has much higher toughness, but generally, as mentioned, when we talk about ceramic, we need to use ceramic carefully, not for tensile application, right? It is more for compressive and other properties, because it is by nature the material is weak in tension. Okay, maybe I might just skip this. This is just on transformation toughening, a little bit of theory, self-healing property. The tetragonal structure actually has the ability to transform back to monoclinic upon receiving some stress, like a propagating crack. So what happened is that, remember earlier the theory I mentioned about volumetric expansion when it goes from tetragonal back to monoclinic. So when there's a crack trying to propagate through a tetragonal structure, the tetragonal particles will absorb this stress and will transform. And when it transforms, remember the transformation incurs expansion. So this particle will expand. That's why you see this circle, this darkened circle is slightly bigger than the tiny, this tetragonal circle. And because the impulse only in the vicinity of the crack is transformed, there is a back stress pushing onto the crack to close up the crack. And therefore, it self-heals. It stops the crack from propagating. And this is the uniqueness of tetragonal zirconia. This is just experimental evidence showing the tetragonal, the transformation toughening. This is an indentation, and you can see swelling. You don't see the crack. Normally, there's crack coming out from the four corners of Vickers indent, but you don't see this crack because there is back stress by the transform particle that impose onto this. And of course, this area is still tetragonal. This area has been transformed. So therefore, the only way is go up. So this is actually coming up from the surface. And that's why we see this bulging effect. And the load that we use or I use for this test is very high, 100 kilogram force. Okay, and you can see no spalling. And basically, you have curvature of this indent showing that the material is very tough, okay, very tough material. And this is basically tetragonal zirconia. This part of my PhD work some 20 years ago. Okay, we also show that this is just microwave versus these are relative densities. So I think you've seen this. Okay, so we know that it's better in terms of modulus, also better in that sense when we microwave. Hardness as well, much better than conventional in that sense. We also work on solid oxide fuel cell. One of my students did this a couple years back. Basically, she compared the conventional versus microwave. This is Scandia dope zirconium. So for solid oxide fuel cell application, as we know that sintering of this ceramic SOFC, they always exhibit very large grain size because we need to sinter at very high temperature to get a dense body. So we actually adopt microwave at low temperature. And what I want to highlight, not to go in very detail, is to look at the grain at low temperature itself. Okay, we're not focusing at the high temperature end, at the low temperature end. This is the conventional heating. If you look at just at 1350, very large grain, look at the size 10 micron. And if you look at this we're looking at a fraction of that size, 10 to 15 microns in terms of diameter of the structure. But when we compare with microwave at the same temperature, you look at it, 4 micron, this is a fraction of 2 to 3 microns. Again, 1/5 in terms of microstructure. And in this way, we are able to make a strong SOFC in that sense. Not just able to perform its ionic conductivity can be improved, but at the same time, it is also strong. Okay, some application, I'm almost coming to an end. I know I got 1.5 hours. I think I took more than that. I apologize for that. So these are some application of zirconia. You'll see there's grinding media, which some of you all probably has worked with, use them. You can use it for sleeves, bearings, mention about sleeves, pumps, seals, femoral heads we've seen earlier for the total hip replacement. Knives, cutting tools, this is something that I made long time ago. Blades, these are blades, shaving blades. Cutting tool which I made for industry to replace their metallic tooling. One of these is just, maybe this is about 10 centimeter, 10 millimeter, 1 centimeter. So we are looking at 1 centimeter in terms of the length here. So it's a small tool that used for semiconductor cutting. So each one of these small insert costs about 200 ringgit, roughly about maybe $50 US. So this is something that I've made for a client some time ago, and we can use this also cutting tool bit for cutting metals. And of course, the famous implant. We cannot run away from this. If you need to put in, if you lose your tooth in between and you need to look nice again, then you will have to consider implant. You cannot run away from this. This is some latest work that we are doing with a company in Thailand, microwaving porous zirconia. So basically, as you can see, very beautiful, precise control of porosity. So we hoping to use this as porous implant, okay, for areas as scaffolding, so that we allow ingrowth of the vessels, blood vessels, and so on. So this is still at the development stage. The company has made a lot of cutting tools, drill bits, especially for dental. They used to do metallic implants. They make all these by themselves. And, I got involved with them, giving consultancy on zirconia, looking at what is the best condition to sinter them, either microwave or conventional. And they have made a series of tools. Okay, these are used for drilling purposes. Okay, drill bits. Right, as you can see, they are drill bits. This is to basically widen up a hole or you can have drill bits of various diameter. This is 2.8 diameter. And of course, you have various other shapes for various other purposes as well. Okay, so these are drill bits and they are sold mainly in the Europe. Okay, in summary, basically microwave serves, right? It saves energy, it's effective, rapid, versatility, economic, and selective heating, as we can see. I just presented to you. Okay, just before I end, maybe I just want to show you a video. Okay, I just want to show you a video of zirconia implant. So it can be a little bit disturbing. If anyone can't stomach the video, then you can just turn your video off. But let's have a look at this. Okay. Okay, I got to share the video screen. Let me see. Give me a second. Huh?
Yes, sir.
Okay, I'm trying to find how to share it. Huh? Just give me a second.
You can directly play it over the screen, so it is as it is visual only.
You can. Okay, let me try and see. Can you see this video?
Yeah, not video, so your screen is visible. You can directly start the video. So, and
Okay. Okay, you can see now?
not you need to, I think, minimize this presentation. Minimize, yeah.
You can see it now?
Not now, sir.
Can you see it? No.
No, not there, sir.
No, not you're not seeing it, huh?
Yeah. It is not there, sir.
Okay, wait. Let me see. I got to.
I think you need to share it again.
Yeah, just 1 second.
Yeah.
Okay, can you guys see this?
Yes, sir. It is. Yeah, sir. It is visible now.
Okay. So I basically it's a tooth extraction and then replacement with artificial tooth. So basically, the dentist will see if there's enough bone mass in order to put the implant.
Yes, sir.
Okay, a pilot hole is being made. This is basically zirconia drill bit, 2.3 diameter. Okay, good position. Slightly bigger hole. So this is trading to make the trade in the bone. And this is the zirconia implant.
Okay, sir.
Good as new.
Yeah, yeah, exactly, sir.
All right. So before, after.
Yeah.
Okay.
Yes, sir.
Okay, just 1 second. Okay, can you guys see the screen?
I think it is not there.
Okay, but all right. I think there's this thing is a little bit not responding, but it's fine. My last screen is just thank you. So I come to the end of the presentation already.
Okay, sir. So, I think it was a great, wonderful discussion and talk you had, sir. And all the our participants have responded positively that it was amazing and nice.
Okay, it's a
I
pleasure.
would
It's a
like to
pleasure.
read some questions. Yeah, yeah, sir. It's a pleasure for us also. So one of the query asked by the participant, I need to just read it for you. What are the main difficulties during the ceramic processing in microwave as the ceramic are transparent to microwave energy?
Yeah, I think that is the trick. If the ceramic is transparent to microwave, you will definitely won't be able to use microwave because you will not couple microwave. You need to have a ceramic material that can couple microwave. Some ceramic couple microwave very quickly at low temperature. You don't need the help of susceptors. but some ceramic couple microwave at slightly higher temperature.
I think some connectivity is there, so we need to look into that. Our next speaker has already joined us. Okay, so we will start our next talk in a couple of minutes. I think some connectivity is there. So, however, it was already done from Professor Ramesh. Okay, so some queries I will just forward to him. So whatever the response we will get from him, I will share with you all. Okay. So I think Dr. Talochan Singh is there. I think am I audible to you, Dr. Talochan? Hello.
Hello.
Yeah. Dr. Talochan, am I audible to you?
Yes, sir. Yes, sir.
Okay. So in this way, we can start our next session. Dr. Talochan Singh will deliver his talk on his research interests and work he conducted. Before invite him, request him to deliver his talk, I would like to share some brief about him. Dr. Talochan Singh did his master's and doctorate from IIT Roorkee, and his basic research interests are related with the hybrid machining processes, development of hybrid manufacturing setups, non-conventional machining, composites, and smart materials. He also owns a patent on his self-developed hybrid manufacturing setup. Uh, he has published more than 20 plus articles in the reputed international and national journals and various book chapters. He authored several books also, and there are about 200 plus citations into his Google Scholar account and research lab. So I would like to invite Dr. Talochan. He's presently a postdoctorate fellow at IIT Bombay. So Dr. Talochan, please hold for 2 minutes. Professor Ramesh Singh has already connected to us, so at least we can have the complete end.
Okay.
Yeah, sorry about that. It was the system just got hanged.
Yeah, it was something there. So I thought some connectivity issues there. So please, sir, you can complete your that. It was
I was just mentioning that with the question that you posed just now. Sometimes the ceramic may not couple the microwave at low temperature, so you need to use susceptors, heat up the chamber, and once the temperature is about 200-300 degrees, the ceramic would be able to couple the microwave. If the material is transparent to microwave, then it will not basically capture the microwave, and you can't heat it up. But most ceramic material they couple microwave. So there's no problem. Only thing is that you may need to experiment with it in order to find what would be the best condition for microwave sintering.
Yes, sir. Thank you, sir, for this clarification over the query. I need to read the last query asked by the participant, Manish Bhargava. He is asking that is there any reference to key chemically equivalency of material with human body parts?
There's no references. You can basically read up. There's a lot of article on the use of materials for biomedical application. There are actually guidebooks or encyclopedia which are published. So these are all good references. I mean, I don't have a specific guide that can help, but certainly you can always the participant can always check with any textbook on the biomaterials for biological application, and you can see all sorts of material being used for this sort of application.
Okay, sir. Thank you, sir. The last query I need to read, sir. What can we add to aluminum powder to make it more responsive to microwave?
Aluminium or alumina?
Yeah, aluminum powder.
Okay.
It must be, I think, aluminum oxide. I think he want to write. I think alumina.
Yeah. So aluminum oxide normally they couple microwave, but you need to use susceptors at low temperature at initial stage. The other, as I showed earlier, the other option is to mix a small amount of transition metal like copper oxide or manganese oxide. Now, these transition metal, they couple microwave very easily. And so you can have volumetric heating taking place at low temperature. And the body can heat up quickly. Okay, so these are some of the options that you can consider.
Okay, what about if we talk about the pure aluminum powder? He's asking again.
Pure aluminum powder, it depends because you need to experiment with the material in order to see what would, under what condition the material would actually couple microwave. You see, microwave energy, it relies on the dielectric properties of the material, and not a lot. If you look at industry application, most of the time microwave are being used for drying purposes. Okay, because it couples, when we talk about drying, it reacts with liquid, and water couples microwave fairly easily. But for other application, it's all like in terms of laser welding, hybrid welding. It is not at commercial scale because there's a lot of issues with microwave as well, because there's a lot of uncertainties how materials would behave under microwave condition and so on. So a lot of it, I would say, it's still at research stage, and whatever the condition that the material needs to be used, that it needs to be experimented with. So it's very difficult to say that there is a fast guide on if you are using aluminum powder or if you are using metal powder, what would be the method that you can use, right? So because this area, as I said, it's very much material dependent.
Okay, sir. I think you have covered so many the queries. You have responded so many the queries asked by the participants.
No problem.
It was a wonderful, sir. It was a great pleasure for to have you during this particular session. So thank you so much, sir. Thanks a lot.
No problem.
Please do over here. Thank you, sir.
Yeah, thank you for having me. Thank you for having me here in this presentation, and thanks, Ravi, for inviting me and your organizing team. Thank you.
Thank you. Thanks a lot, sir. Thanks a lot.
Okay, have a nice day, everyone.
Yes, sir. Please. Thank you. Dr. Talochan, actually, we had our last speaker in between. So, I was just saying about the present affiliation of Dr. Talochan Singh. He is presently a postdoctorate fellow at IIT Bombay and working on the same interest, hybrid manufacturing setup development and research into that. So, Dr. Talochan, I would like to request you, please, you can share your screen and start your discussion. Please. Welcome, Dr.
Okay. Okay, my screen is visible.
Yeah. It is completely visible. You can start.
Okay. Good afternoon, everybody.
Good afternoon.
I am going to present a talk about micro manufacturing through hybrid ECDM processes. So, in this talk, I will try to focus on process conceptualization, how we have to drive the concept of hybrid processes. What is the need behind the derivation of these particular processes? And more specifically in concern of micro manufacturing, what is the need to drive these hybrid machining processes? So in this topic, I will try to cover two aspects. First here, I will try to cover about the hybrid ECDM processes, and second one, I will try to cover in concern of micro manufacturing. What is the need of this process? So in this slide, I would like to explain what is the definition of hybrid. Basically, hybridization is there is two terms. One is a combination, and second one is a better characterization characteristics. So a thing made through the combination of two different elements in order to get better characteristics from the parent elements is known as a hybridization. So this concept has been already introduced in several sectors like agriculture, automobile, manufacturing, aiming to get different outcomes. In case of agriculture, our objective is to get the nutrient food with a high productivity. In automobile sector, we have introduced this concept by the aim to save hundreds of pounds at the fuel stations. By the concern of manufacturing sector, our main aim is to reduce manufacturing cost. By reducing the manufacturing cost, we can easily provide a product to the customer end. And second one is to improve the process capability. I mean to say here in terms of material and in terms of process shape complexity. Here the process capability implies first one is in concern of material as well as in concern of shape complexity. So the development of hybrid seeds played a very prominent role in the introduction of green revolution of India is a big example of the concept of hybridization that is introduced by the Punjab Agriculture University during the Green Revolution of India. So as per the concern of manufacturing process, so here in this slide, I would like to talk about the manufacturing process and where we can introduce this concept of hybridization. Okay, as we all know, manufacturing is simply a step which transformed a raw material into the final product. There are 2 points. One is a raw material at initial and the final, and we have to get the final product. But the stage of transformation is very important. And this stage is known as a manufacturing process. In manufacturing process, basically manufacturing process is governed by the machine tool, and the machine tool is particularly operated by two components. One is an operational tool and another one is a control system. Well, I would like to explain this particular two concepts by using the example of electric discharge machine. For example, I think everybody is aware of the electric discharge machine. Okay, I want to produce some hole by using the electric discharge machine. When I want to produce some hole by using the electric discharge machine, there is one operational tool and another one is control system. Okay, the discharge will happen between the two electrodes through the dielectric that will be placed in between the two electrodes. The production of a cavity by the use of discharge, by the use of thermal energy, implies the role of operational tool. While when my desire is to produce that cavity up to 3 mm, then the problem is here, the problem is this, how we have to channelize that particular energy up to 3 mm for the production of hole up to 3 mm that we can control by using the control system of that particular EDM machine. So in this way, we can produce a particular product by using two things. One is operational tool and another one is control system. By modifying the components of these two elements, operational tool and control system, we can save the time. Ultimately, we can save the energy consumption that will be used to produce a particular hole, and ultimately we can improve the production rate. What? Here the question is this, where we have to introduce the concept of hybridization in concern of manufacturing process. Okay, so in case of operational, in operational tool, we can introduce the concept of hybridization by introducing new concepts. In case of electric discharge machining, when we talk about the deep hole drilling by using electric discharge machining concept, then at that time there is so many problems. Evacuation of dielectric medium, replacement of dielectric medium, as well as the evacuation of sludge from the bottom of the hole. Then at that time we have to make some modification in operational tool. Then we can apply some ultrasonic assistance magnetic field in such a way we can modify operational tool to to improve the process performance. In such a way, we can say we have an option, we can apply the concept of hybridization in operational tool instead of the control system. So in this way, we can improve the production rate as well as we can overcome the limitations that comes from the, in case of machine complexity, system complexity. Another thing, when the product will be produced, then at that time, we have to measure the quality of product. And our desire, we like to meet the specifications of customer. Then when we have to meet the specifications of the customer, then we have to minimize the when we have to reduce or eliminate the errors that will come into the final product. In such a way, we have to modify, we have to introduce the concept of hybrid machining processes in operational tool of the machine tool, while the aiming to get the quality of the, to improve the quality of the product. So this one is the entire concept of manufacturing process, and where we can introduce in the entire chain of, in the full chain of manufacturing process, where we can introduce the concept of hybridization. So the need of hybridization in context of manufacturing process, as I told you in previous slide, first one is we have when we have to improve the production rate. Second one is when we have to improve the quality. And first one is to meet the specification of the final product by reducing the rejection rate, as I told you in previous slide. And second one is to improve the process productivity, repeatability, and accuracy. And third one is to improve process capability to fabricate complex structure over advanced materials. So by aiming, these are the needs. So that's why we have to hybrid the manufacturing processes. And this definition, these lines are dedicated, where we can introduce the concept of hybridization. A concept of hybridization in manufacturing process can be introduced by integrating the features of two or more than two operational tools. So as I told you in previous slide, we take the example of the integration of two energies. One is EDM and another one is assistance of ultrasonic vibrations through into the EDM process in order to improve the process capability when we have to drill the deep holes. Another one is there are so many manufacturing processes. So there are so many manufacturing by using these manufacturing processes we can get the final product. So in today's discussion, I will try to focus on material removal processes. And in the material removal processes, there are two types of machining processes. One is conventional and another one is non-conventional machining processes. So my talk will be focused onto the hybridization of non-conventional machining processes, and more specifically, I will try to focus on electrochemical discharge machining process, that is a derivation of two non-conventional machining process. One is electrochemical machining process and second one is electric discharge machining process. So this one is my first concept that I will cover in my presentation, and another is micro manufacturing. As I told you in very first slide, my topic will be focused on the micro fabrication. So what is a micro fabrication? As you can see, the role of micro-sized products in electronics devices. The size of pen drive was big in 2004, but with the passage of time, the size get reduced because of the development of micro-sized products. Why micro-sized products? Because there is a necessity to save the energy, material, and space. These things motivated us to develop the micro-sized products. But as per the concern of present trend, in concern of micro manufacturing, the trend is shifted towards the development of microfluidic chips, because they have widespread requirements in applications in like biomedical testing, food engineering, biochemistry, molecular biology, drug testing, point of care, and cell analysis areas. Because of these applications, the trend of micro manufacturing is shifted to develop the microfluidic systems. So as per the concern of the fabrication of microfluidic devices, there are basically, in manufacturing point of view, there are two important aspects. First one is micro feature. What kind of feature that we have to make over the work material. And second one is material. As per the concern of previous research articles, researchers used polymers, PDMS, silicon, and glass materials to develop the microfluidic devices. As per the concern of micro features, they engrave micro holes, micro channels, micro slits, and surface texturing over the different materials to get the particular in particular in order to get the specific application in particular material. As per the concern of material, nowadays the glass material gets most popularity, while in comparison to other materials like PDMS, polymer, silicon, because glass possesses chemical and heat resistance. It provides optical transparency, high temperature stability, high hardness, and because of these properties, the glass material is generally used to fabricate the microfluidic devices. But as per the concern, when we have to fabricate these micro features over the glass material, then micro machining can provide better solutions to develop all these features over the glass materials. There are various options that are available to develop, that can develop micro size features on glass material. As per concern of non-conventional machining processes, we can use ultrasonic machining process, but this process is limited in terms of features, because by using this process, we can only machine micro holes and micro channels over the glass material. As per the concern of abrasive jet machining, we can additionally machine micro slits along with the micro hole and micro channels, but by using laser beam machining, we can produce micro holes, channels, surface texturing, and micro slits. By using laser beam machining, we can get all the four features, all the four basic features that are essential for any microfluidic device. While in concern of chemical machining, we can only produce micro holes and micro channels. And there is another hybrid machining process, that is electrochemical discharge machining, that is basically combination of ECM and EDM. By using this process, we can machine micro holes, micro channels, micro slits, and we can engrave surface textures over these features that have been machined through by using different variants. So now we have in market, two competitors. First one is LBM, laser beam machining, and another one is ECDM. Now we have two competitors. By using both the two, we can machine micro holes, micro channels, micro slits, and surface texturing on glass material. So now there is a selection. Which one would be the best? So as per concern of the selection criteria, I have selected in my work electrochemical discharge machining. Why I have selected? Because in comparison to the laser beam machining, it provides micro level accuracy and it having ability to machine complex shapes. And third one is it having low fabrication cost. This one is very interesting point, because laser points high fabrication cost, and another one is low maintenance cost in comparison to the laser beam machining. So that's why I have chosen electrochemical discharge machine to fabricate micro features over the glass material. So basically, what is ECDM? ECDM, this one is a basic configuration of the ECDM, and ECDM basically hybrid process that integrates the feature of two non-conventional machining processes such as electric discharge machining process and electrochemical discharge machining process. And you can see in this figure, it consists of two electrodes. One is a tool and it is a cathode, and another one is an auxiliary electrode. Both are immersed into the electrolyte. This one is electrolyte and this one is electrolyte chamber. And both the electrodes are connected with a DC power supply. Okay, in this way, electrolyte completes the entire circuit, and we can say this one is an electrochemical cell circuit. In other words, we can say this one is an electrochemical cell circuit. And how it will work, I will explain next slide. And this one is an energy generation and channelization in ECDM process. First concept is how the energy will be generated in electrochemical discharge machining process, and how it will channelize over the work material in order to get the specific shape. As we can see in this figure, when the electric potential will be applied across the two electrodes, then at that time the electrolyte that will be present in between the two electrodes, the electrolysis will be start. The first point is electrolysis. Because of electrolysis, the electrolyte will split in the form of ions. After that, the bubbles will be nucleated from the two electrode by following this chemical reaction. In initial stage, the presence of water, here in this case I have used alkaline electrolyte, NaOH, sodium hydroxide. The hydroxide will split into form of sodium ions and hydroxyl ions, and the water will split into the form of hydrogen ions and hydroxyl ions. Because of this reaction, at the cathode, the hydrogen bubbles will be nucleated from the surface of the tool electrode. After the collisions of these bubbles, the bubble gas film will be formed over the tool electrode, and it will cover the entire surface of the tool electrode, which will be dipped into the electrolyte. As we can see, these are the images that I have recorded by using the high-speed camera. At this point, the tool, the electrode potential is not supplied here, but in this case, when the electrode potential is supplied, then at that time the gas will covers the entire surface of the tool, which is dipped into the electrolyte. In this case, the gas film there is a growth of gas film, and after that, because of unstable state of the gas film, the high electric field will be set up across the surface of the tool electrode as well as into the very first layer of the electrolyte. Because of this spark discharge takes place from the bottom edges of the tool electrode. When the spark discharge will take place, then the value of current will be decreased, and the position of the discharge will change, as we can see in these images that have been recorded by using the high-speed camera, and this position of the spark discharge will change. And after that, when the workpiece will be placed in close vicinity of the tool electrode, underneath the tool electrode, then what will happen? This one is the image, the optical image that has been recorded after the machining of 100 microsecond, and there is just mark of the, you can see here, there is just mark. This one here, just mark of the energy that is being channelized by the spark discharges over the work material. But after 200 milliseconds, there is a more material removal rate in such a way, this one is the inner diameter where the tool will be placed over here, and in this just we can estimate that how the energy will be channelized. Initially, the spark discharge will take place from the bottom edge of the tool electrode just because of high electric field intensity over the edges of the bottom surface of tool electrode. After that, the energy will be channelized toward the inside of the tool electrode, inside of into the center portion of the tool electrode. So in this way, the material is removed from the entire bottom surface of the tool electrode, as we can see in this figure after the machining of 1000 milliseconds. So this one is a slide which is dedicated to explain the energy generation and energy channelization in ECDM process. After that, this slide is introduced about the little bit history of the ECDM process by using the electrochemical discharge energy. Karafuji in 1968 first time reported about this process, and by using this process, Karafuji machined micro holes over the glass material. And this process is presented by several names, and this process is also presented by spark assisted chemical engraving, electrochemical spark machining, electrochemical arc machining. When we have to machine the metallic components. When we want to machine the metallic components, then at that time this process is termed by the name of electrochemical arc machining, and another one is discharge machining of non-conductors, and last one is electro-erosion dissolution machining. By using this electrochemical discharge energy, we can machine various micro features by using different process variants of electrochemical discharge machining process, and these are the process variants. First one is electrochemical drilling. And using this process, we can produce holes. It may be through or blind, and we can produce holes cylindrical, conical, or spherical. And these are the options. By using different options, we can fabricate variety of micro holes. So that's why here I want to mention one more thing, that this one is very good in when we have to fabricate microfluidic devices, because as per the concern of microfluidic devices, when sometimes we have to fabricate some specific type of reservoirs, then at that time we have to fabricate different kind of micro holes like cylindrical, conical, or spherical. But the laser beam machining is limited to fabricate only one type of structures, that you can say our desire is to form the cylindrical surface. But here the important feature is that we can also fabricate spherical and conical holes in controlled manners. But in case of laser beam machining, we can get the conical shape of holes, but that will not be in controlled manners. So that's why this one is the beauty of this process. And after that, by using the milling variant of this process, we can produce micro channels, micro grooves that may be straight or curved. And after that, by using the trepanning process, we can make the deeper holes, and turning process, we can make the micro grooves on cylindrical surfaces. And there are other variants like electrochemical discharge drilling, dressing, wire electrochemical discharge machining. The concept is same. In all these variants, we can use these variants to solve the different problems by using one common energy, that is electrochemical discharge energy. So this one is a beauty of this concept, that has been coupled by using two non-conventional machining processes. One is electrochemical machining and another one is electro discharge machining. As per the concern of cost, it's a very cheap process as compared to other non-conventional machining processes. So this one is a setup, ECDM setup that I once fabricated during my PhD work. This setup we can use to fabricate micro channels, micro holes. Even this setup we can use to produce micro slits. And this one is, as I told you, this one is a DSO to record DSO, stereo oscilloscope. Basically, this one is an oscilloscope that we can use to process the signals and monitor the online conditions. And this one is a DC power supply that is coupled with the tool, and this one is the auxiliary electrode, and the electrolyte will be placed here in the electrolyte chamber. And this one is a photographic view of the ECDM machine that I have used to fabricate the micro channels. And the movement of X, Y, and Z axis is controlled by the controller, and controller is programmed by the programming unit. And this one is a setup that I have used to fabricate the micro channels on glass material. As I told you in this slide, the energy is channelized from the side edges of the two electrode. This one is a basic problem in electrochemical discharge machining. The energy is channelized from the bottom surface of the two electrode instead of the entire bottom surface of the two electrode. So in this way, when we talk about the drilling operation, then at the time there will be problem to machine the deep holes. We can't machine the deep holes because the energy will be channelized from the bottom edges. So in this way, there will be problem during the feeding of the two electrode into the work material. In other sense, we can't get the exact shape of the micro feature in terms of when we talk about the micro channels. So that's why there needs some modification over the surface of the tool electrode that we can get the energy channelization from the entire bottom surface of the two electrode from the very first time of the machining. In this phase, after, as we can see here, after 1000 millisecond, we are able to get the material removal from underneath the entire surface of the two electrode. But I want to get this condition from the very first point. So what we have to do? Then we have to modify the geometry, modify the shape, modify the morphology of the tool surface that we have used in the ECDM process. So what we have did, so that's why in order to eliminate this problem, I have used texture tool, and this one is a setup that I have used to fabricate the texture tool. Here we can see in texture tools what I have did. I have made some rough surface over the tools. As you can see here, this one is the same image of the tool. By using the thermal energy, by using the electric discharge machining process, I have developed rough surface over the tool, and this one is the surface profile of the texture tool. As you can see, there are sharp edges and there is a cavities over the surface. In next slides, we will see how these cavities and these sharp edges will help us to produce the smooth surface. And this one is a tool and work material interaction mechanism during the microchanneling with ECDM. When I will use the smooth tool, then what will happen? When the tool electrode will be inside the work material, then it will make the direct contact from the leading phase, as well as it will make the direct contact with the bottom surface of the work material. There will be no gap. So what will be the limitation of this process? First one, in terms of energy channelization, when the tool will be in zero contact with the work material, then at that time the bubbles, the gas will not be formed from this area, and the tool will not lead in this direction. So there will be limitation for the feeding. And another one is when the tool will be in zero contact with the work material bottom surface, then the discharge will produce from this place instead of this, because there is no gap for the film formation. So that's why the channel shape, the micro channel that will be formed in this direction. The micro channel that will be formed in this form, because the energy will be more concentrated here and here. So that's why there is a problem. There is a problem with smooth tool. But in case of texture tool, when we use the texture tool to fabricate the micro channel, then at that time it will help to make the micro cavities with the leading phase as well as the bottom phase. So these micro cavities will help us to replace the electrolyte, help to flow the electrolyte, and it will also help to evacuate the debris that will stay here after the processing, after the material removal action. In this way, we can also get the discharges from these points, these sharp edges. So in this way, we can say by using the texture tools in this process, we can distribute the electric field, the constant electric field from the entire bottom surface of the tool electrode instead of the edges of the tool electrode. So that's why we can get the discharges from the entire bottom surface of the tool, and we can get the smooth surface at the bottom of the micro channels. So this one is a mechanism, this one is a kinematics, how the interaction will take place when we will use the smooth tool and the texture tools. And these are the results that I have obtained by performing the experiments by using both the texture tools and smooth tools. In case of smooth tools, and you can see the material removal rate is very low. And you can see here, the material removal rate is very low. But in case of texture tool, when I have used the texture tool, the material removal rate is higher. After 58 volt, the material removal rate for both the tools get decreased because of the aggression of electrochemical action and because of the production of more gas bubbles surrounding the tool electrode. But this material removal rate is higher in case of texture tools in comparison while compared to the smooth tools. As per the concern of depth of the microchannels, the texture tools provides more deeper microchannels in comparison to the smooth tools. And width over cut smooth tools provides more wider microchannels in compared to the texture tools. Because the reason is that in case of texture tools, the energy is channelized either over the leading face and the bottom surface of the tool electrode. But in case of smooth tools, when there will be direct contact between the leading face and work material and between the bottom face and the work material, then at that time the gas film formation will start. I will explain here. The gas film formation will start from the side edges, here and here. Then at that time the spark discharge takes place from the bottom edge of the side edges of the tool electrode instead of the bottom and leading face of the tool electrode. So in such a way, the microchannel width get increased in case of smooth tools. But in case of texture tools, the energy will be channelized either from the bottom surface of the tool electrode or from the leading face of the tool electrode. As per the concept of surface roughness, the surface roughness is reduced by using the texture tools, but in case of smooth tools, surface roughness is very higher as compared to the texture tool. And this one is a signals that has been recorded by using the digital storage oscilloscope. Basically, these signals we can use these signals to monitor the actual behavior of ECDM process. In case of smooth tools, when the voltage is very low, 50 volt, there is a inconsistent up and downs. These up and downs, I have mentioned these up and downs as a discharges. These up and downs indicates the discharge characteristic. In this case, you can see their up and downs are not constant. But in this case, the up and downs are stable. What it means, the discharges provided by the texture tools are consistent. How it possible? Because of the same electric field intensity, because of the distribution of same electric field intensity over the entire surface of the texture tool. And second reason is that the development of thin layer over the surface of tool electrode. Because the breakdown of thin layer will result into the formation of consistent discharges. And another point is here that discharge characteristic, we can characterize discharge characteristics by using 2 points, by two indicators. First one is discharge intensity and second one is consistency or frequency of discharges. By using the texture tools, we can achieve more consistent discharges with low intensity. But in this case, smooth tools, what we have obtained, the discharges were inconsistent, first point, and another one point, the intensity of discharges were very high as compared to the texture tools. Why this so? Because of the formation of thick gas film over the tool electrode. But as you can see here, there is no space for the film formation. Then where the film will form? The question is this: where the film will form? then there will be more space for the film formation, and the film will be formed from the side walls of the two electrode instead of the leading end bottom phase. So that's why the breakdown of these thick gas films results into the formation of high intensity inconsistent discharge. Why this one is inconsistent? When the high intensity discharge take place, then there will be the bursting of thick gas film. Because of the bursting, because of the breakdown of thick gas film, the energy that will be produced at that particular point will provide the high temperature. Because of that high temperature, the electrolyte that will be present around the two electrodes will get evaporated. Because of that evaporation, the bubbles will be more produced around the two vicinity in such a way, the bubbles, the efficiency of film formation and electrochemical reaction will get decreased. So that's why the consistency in discharge characteristics will get deteriorate when we use smooth tools. This one is a basic reason. And as per the concern of applied voltage, when we increase the applied voltage, then at that time the intensity of discharges will increase for the both tools. As you can say, for the intensity of 81 volt, in further 66 volt, it is 138 volt. And same here, the intensity of discharge characteristics increases with an increase in applied voltage. Here the intensity is 74 and here 115 volt. So why is so? Because when we increase the applied voltage, then at that times the bubbles accumulate, the accumulation rate of bubbles will be more. Because at higher voltage, the electrochemical reactions will get accelerate because of the high potential difference. And because of that high potential difference, the bubbles will get accumulated more and more for the same time duration. So in this way, we get a thick gas film. We get a thick gas film by increase the voltage in comparison to the low applied voltage. So there is another most important point. By increasing the voltage in case of smooth tools, the intensity increase, but the frequency of discharges get deteriorate. There is an inconsistency in discharge characteristics get increased. But in case of texture tools, there is more consistent discharges. Even the applied voltage get increased. What it means? It means that the texture tools are now producing the gas film that is controllable in that particular limit. So that's why it produces consistent discharges with high intensity. So this one is a difference. This one is a difference that you can see here. These are the actual conditions that I have recorded during the processing of borosilicate glass by using both the tools. Here we get the consistent discharges with high intensity. So in this way, we can say when we have achieved this type of discharges, high intensity discharges with high frequency, then it means that we can channelize, we can utilize, and we can penetrate higher energy into the work material. So this one is the advantage of texture tools in context of discharges that directly or indirectly implies the actual condition of machining. And this one is an energy channelization. The title of this slide is energy channelization from smooth and textured tools. There is two figures, and figure A is the cross-sectional view of the microchannel machine with the smooth tool. And this one is a figure that I have captured by using the optical stereo microscope when I have machined the microchannel by using the texture tool. In these two images, you can see clear-cut difference between the performance of smooth and texture tools. In case of texture tools, as I have told you in previous slides, the energy is forced. Okay. Take example here. Okay. There will be a tool, and there will be the tool. Okay, this one is a tool. Okay, and in case of smooth tools, because of high electric field, this one is a cross-sectional view. This one is a cross-sectional view of the tool. And the energy will take place, the spark discharge will take place from this position and this position. Because of this, the material removal rate is higher from these sides. But in this side, the material removal is low. By using smooth tool, we can obtain only humped bottom surfaces, not a smooth surfaces. And the second thing is that when the tool and workpiece will be in zero contact, then at that time after the machine, the sludge will accumulate here. The sludge will accumulate here at these points. At these points, the sludge will get accumulate, and because of the electrolyte, because of the presence of electrolyte here, the spark discharges will take place from these sides, from the side walls of the tool electrode. So in this sense, this shape of the tool electrode, the shape of the micro channel will be like this. Okay, will be like taper walls. But in this case, the material removal, okay, this one is a, let's assume this one will be a tool. Okay, this one is a texture tool. And because of the texture tool will be like this. And because of the uniform electric field intensity, the spark discharge will be produced from this, and this position. Because of this, the energy will be channelized. The energy will be channelized from this, and this point. In this way, the material will remove from the bottom surface will be in uniform manners as compared to the smooth tool. This one is the beauty of texture tools. By using these tools, we can get the smooth surfaces as well as the micro channels with straight walls. But in this case, you can see the entire scenario. And this one is the impact of energy on work material with smooth and texture tools. As I have told you, at initial stage, I have explained two things. First one is energy generation and energy channelization. We can assess the characteristic of energy generation from the discharge characteristic. As per the concern of energy channelization, we can assess the characteristic of energy channelization from the micro feature that we have engraved by using a particular tool, and the surface that we have obtained by using the machining. We can get the impact of energy, or we can get the energy channelization characteristic. In this case, this one is a, in this figure, this figure is a surface morphology of machined microchannel surface with smooth surface, and this is a surface morphology of machined microchannel surface that has been machined by using the texture tool. In case of texture tool, we have obtained smooth surface because the discharge will be produced of low intensity. But in this case, there are some micro cracks, thermal damages, and you can see the surface morphology of the machined microchannel. And in this way, we can say this surface is produced by the high intensity inconsistent discharges. But this surface is produced by the liberation of consistent discharges with low intensity. So in this way, we can gauge the smooth surfaces by using the texture tools, and the surfaces with smooth tools will be full of micro cracks and thermal damages. And after this one is a comparative study and that I have performed to differentiate the smooth and texture tools. After that, I have selected texture tools to machine the micro channels over the glass material. Then at that time, I have selected some parameters, 5 parameters on the basis of these 5 parameters. I performed some experiments by following the central component design concept of RSM, response surface methodology. And from that results, I have drawn some models in terms of surface roughness, material removal rate, depth of penetration, and width overcut. By using these models, I have plotted these graphs, and this indicates that the performance characteristics of texture tools. Here we can see the effect of applied voltage on material removal rate and depth of penetration. As you can see here, with an increase in applied voltage, when we will increase the applied voltage, these experiments I have performed by using only texture tools. You can see there, with increase in applied voltage, the material removal rate get increased. But at this point, the material removal rate get increased. After that, with an increase in applied voltage, the depth of penetration rate get decreased. But as you can see in concern of material removal rate, the material removal rate is increasing, but it decreases little bit after this particular point. Okay, the reason is that when we increase the applied voltage, then it will accelerate the electrochemical reaction. Because of the higher electrochemical reaction, the bubbles that will accumulate over the surface of the tool electrode will be more, and it will help to make the thick gas film over the tool electrode. And the breakdown of that particular gas film, the breakdown of that particular thick gas film liberates the high intensity discharges. Because of the liberation of the energy liberation by these high intensity discharges, the material removal rate and the depth of penetration will be high. But after 59, 58, 60 volt, the end of depth of penetration will get decreased, and the entire energy is utilized to increase the surface roughness and width overcut. Because the reason is that the spark discharging initiate from the side walls of the tool electrode instead of the bottom surface. So that's why after 60 volt, the texture tool are also not able to penetrate the discharge energy from the bottom surface. After 60 volt, it will also show same effect as we can see in case of smooth tools at lower voltage. So I think here the 60 voltage is appropriate to conduct the experiments for further stages. And in the case of width overcut, the width overcut increases linearly because of the accumulation of bubbles at the side walls and the initiation of spark discharges from the side walls of the tool electrode instead of the bottom surface. Surface roughness is initially decreased. Why it initially decreased? And after 50 voltage, it increased. Why it's so? At initial stage, because of the texture tools, I have used the texture tool. I want to show here the shape of the texture tools will be like this. Okay. And at lower voltage, the spark discharge will take place from the bottom edge, from the bottom fingers of the texture tool. Are you getting my point? Okay. From these points. Okay, when the discharge will take place from this place, and it will remove the material in this fashion, and in this fashion. Okay, and the final surface that will be produced like this. Okay, So this one will be a rough surface at lower applied voltage. When the voltage will be increased, then the surface roughness will decrease because the discharge that will be produced from these fingers will cover the more area. It will cover the more area like this, like this, like this. And at near about 58 volt, the area will be like this. The distribution of the energy from the bottom surface of the tool will be same. So that's why we can get here the smooth surface comparatively to the other applied voltage conditions. But after that, when after 58 volt, the energy will be increased because there will be thick gas film, and when the thick gas film will be break down, then the intensity of the spark will be more, and it will cover the more area but more depth, deep surface and deep humps. Okay, and these surfaces will be more deeper when the applied voltage will be increased. So in this case, so in such a way, the 58 volt is effective while in concern of the surface roughness. And second one is the pulse on time. When we increase the pulse on time, basically there are two phases. In ECDM, we can use either DC continuous power supply, and we can also use pulse power supply. The difference is this: in case of pulse power supply, we supply the power in terms of applied voltage and current in small pulses. Why it is so? Why we prefer pulse power supply over the DC continuous power supply? Because in case of DC power supply, when we supply the power continuously, then at that time the breakdown of gas film will be continued, and the sludge and debris will accumulate at the bottom surface. Because of the accumulation of the bubbles and debris and the electrolyte, passivated electrolyte at the bottom surface of the tool electrode, the discharge energy will not penetrate into the work material surface. And the second point is that I want to mention here. So when we supply the DC power supply in continuous manners, then the spark discharge will be take place. It may be take place either from the bottom surface, either from the side walls of the tool electrode, but it will be in continuous manners, and the tool will get hotter. The temperature of the tool will get increased. Because of that, the electrolyte that will be present into the close vicinity of the tool electrode, the temperature of that particular electrode get increased. Because of the increased electrolyte temperature, the evaporation of electrolyte will get, the evaporation rate of the electrolyte will get also increased, and it will also, in further stages, it will also affect the level of electrolyte. When there will be more evaporation of the electrolyte, then the electrolyte level will get decreased. Because of this, the change in electrolyte level in ECDM process, the processing conditions of the electrochemical cell circuit will also get changed. Because of these changes, the entire circuit, entire behavior at same parameter condition that I have initiated from very beginning will be different. So in this way, we can't get the repeatable machining conditions, and we can't get the accurate and same structure throughout the entire machining. These are the limitations of DC continuous power supply. So that's why in general we prefer pulse power supply in case of electrochemical discharge machining process. So in pulse power supply we have two phases. One is pulse on time and another one is pulse off time. Pulse on time is utilized. Basically this pulse on time, as the name you can see here, as the name implies, on. On means when the power is on, means when applied voltage and current is in action. And pulse off time indicates means there is no power. When there is no power, and in some research articles, the pulse of time is referred with the name of cooling time, cooling span, where the cooling will take place. Some of the researchers mention this name with a replacement time, where the electrolyte will get replaced and the new electrolyte will come into the machining cavity. So in these experimentations, I have varied pulse on time from 1 to 5 millisecond. As you can see here, the same results, literally same results here, with an increase in pulse on time, the material mover rate increases initially up to 3 millisecond, approximately 3 millisecond on time. And after that, the material mover rate get decreased, and this increase in material mover rate is utilized to increase the depth of microchannels. As you can see, after that, the pulse on time, beyond the 3 millisecond pulse on time, the pulse on time behaves like a pulse of a DC continuous power supply. After 3 millisecond, when we increase the pulse on time beyond the 3 millisecond, then it will show the same characteristics like the DC continuous power supply. The bubbles will accumulate here, there will be no time for the replacement, and the electrolyte will get evaporate, as well as the level of electrolyte get decreased, and then further proceeds and results non-repeatable machining conditions. As per the concern of width overcut, the width overcut is continuously linearly increases, and as per the concern of surface roughness, the surface roughness is increases continuously, but the width overcut is first decreases, and after this point it increases. And this one is a pulse of time, as I have told you in related to the previous slide. Pulse of time, this one is basically cooling span time. When we increase the pulse on time, from 1 millisecond to 5 millisecond, the material removal rate decreases continuously. Why this one? The material removal rate decreases continuously because for this time period there will be no spark discharges. The time for spark discharge will get decreased. The second point is this: when we increase the pulse on time more, then at that time the electrolyte that will be present into the machining zone will be more. The temperature of that particular electrolyte will be low because of the effective replacement of the electrolyte from that vicinity. In this way, the impulse on time, it will take more time to initiate the electrochemical reactions, and film formation time will also get increased. So in this way, it will provide very low time to liberate the discharge energy over the work material. And as we can see here, the surface roughness also increases because of why the surface roughness is increases. Because as I have showed you here, when the spark discharge will initiate from these fingers, and when there will be high pulse of time, then what will happen here? The spark discharge time will be low. When the spark discharge time will be low, then at that time the energy liberation will be low. Because of that energy liberation, the surface that will be produced by the fingers will be like this. So that's why the surface roughness will be increased with an increase in pulse of time. Next parameter is the feed rate. Feed rate is a very important parameter because it decides, in case of microchannel, it decides the interaction durations between the tool, electrode and work material. As we can see here, with an increase in feed rate, the material removal rate get decreased. When the material removal rate get decreased, why it is so? Because the time duration to liberate the energy the two electrode over the work material will also get decreased. The interaction time between tool and work material also get decreased, and the depth is also decreased. Why the depth is decreased? Because of whether depth is decreased because of the low interaction time. In case of low interaction time, the energy will be provided. So this one is a path where the tool, this one is a tool, and this one is a path, a work material, and tool will, when we have to move the tool in this direction, because of higher feed rate, it will liberate the energy in these manners, but the energy will be low. Because at low feed rate, the dip will be like this, but at higher feed rate, the interaction time is low and the cavity that will be produced like this. So in this way, we have obtained low material removal rate and depth of penetration. So as per the concern of depth overcut, the breadth overcut at the initial stage, breadth overcut is higher, but with an increase in feed rate, it gets decreased, but after that, it also gets higher. Why it is so? Because when the feed rate is low, then at that time the interaction time is low, and the channel surface, the channel upper surface will be like produced like this. In this one is the upper face of the surface of the channel. The top view of the channel will be like this, because energy will be, when the tool will be like this, then it will relate the energy to these points. But because of the stick and jump phenomena, the tool electrode will get stuck here. Because of this stucking effect, sometime it will get bent and it will get from the top, it will get break. Because of this stick and jump phenomena, the top cross-sectional view of the top view of the microchannel will like this. Because of this, the width of channel will be higher at the lower penetration. Another is electrolyte concentration. Basically, when we increase the electrolyte concentration, then at the time the material removal rate get increased linearly, and the depth of penetration first increase, after that get decreased. In case of width overcut and surface roughness, the trend is same. Initially, both are decreased, and after near about 20 electrolyte 20%, the surface roughness and width overcut increases. In case of electrolyte concentration, when we increase the electrolyte concentration, then at that time, there will be more, the current will be passed very fastly, because of there will be some fast electrochemical reactions inside the electrolyte. Because of these electrochemical reactions, the gas film formation phenomena will be fast, and the gas will form over a two electrode will be more quickly. And in this way, the energy generation and energy liberation phenomena both get activated, and high rate both get accelerate in the previous high rate. Because of this, we can get the higher material removal rate and depth of penetration by using the higher electrolyte concentration. But beyond the 20%, the energy is channelized. The energy is channelized from the side walls of the two electrode instead of the bottom surface, because of the accumulation of sludge. Because at a higher electrolyte concentration, the concentration of sodium ions will be more, and after the chemical reaction, the presence of their sodium ions underneath the two electrode will help to promote the electrolyte passivation, as well as to promote the contribution of sludge and debris over the bottom tool electrode. In this sense, the gas film formation will start from the side walls of the two electrode, and the spark discharge will take place from the side walls of the two electrode, and the energy will be channelized from the side walls instead of the bottom surface. And this one is next, as I have told you in previous slides, very first slide, basically we required 4 features in context of microfluidic devices. First one is micro holes, micro channels, micro slits, and fourth important feature that we have required for the microfluidic devices is surface texturing. Why the surface texturing for microfluidic devices? Because in microfluidic devices, more specifically in case of micro mixing problems, when we have to mix the 2 fluids at micro level, then at that time we have to create the turbulence among the fluids. Then at that time we can generate that particular turbulence by providing the textured surface over the surface of micro channels. So this ECDM process also can be utilized to form the micro textures over the surface of over the bottom surface of micro channels. This one is a mechanism. As I told you, the electric field intensity will be higher and the energy will be channelized from the aspiratory sides, and in this way the final we can get the dimples and bumps. So when these dimples and bumps will be in continuous fashion, then we can get the surface texture. We can get the surface texture by using the ECDM process. And in other words, we can say ECDM is very effective to produce a textured surface. The thing is that, as I have discussed in the previous slides, during the evaluation of parametric evaluation, we can get the more surface roughness, low surface roughness. The mechanism how we can get the higher surface roughness and low surfaceness as well as smooth surface, what would be the mechanism behind this, as I have explained. But as per the concern of texture tools, we have to control the energy level. Okay, and we can control that particular energy either by controlling the applied voltage parameter or the concentration of electrolyte. Here, as you can see in this slide, we have varied the electrolyte concentration from 10, 20, and next one is 30, while the other parametric conditions were same. When I performed these experiments, the other parametric conditions, applied voltage was 58, feed rate was 16, P on and T of time was in the ratio of 3:3. But in 10% electrolyte concentration, this surface that has been generated was textured. But with an increase in electrolyte concentration, the smooth surface was produced. But within further increase in electrolyte surface, the surface is smooth. As you can see, this one is a smooth surface. What the thing is that there are some cracks. There are some cracks. Why it is so? So I will try to explain this mechanism, the mechanism behind the formation of these surfaces by using these EDS spectrums. And you can see here the mechanism that will happen here, apart from discharge mechanism, the mechanism of chemical etching, the silent mechanism in this process that will happen here by following this equation. And there will be sodium silicate will be formed in the form of precipitates in the form of solid. And you can see here, this one is a work material, and the work material is borosilicate class, and it is formed by the following components. And this one is electrolyte, and when the electrolyte will be at a higher temperature, when the electrolyte will be present at a higher temperature in this domain, then the electrochemical etching will take place here. The chemical etching will take place here. This one is a silent material removal phenomena that will occur here. Because of this chemical etching, the material will remove here. Because of the material removal in the small chunks, the surface will get smooth. But because of this action, chemical etching action is evident by the elements weights As you can see here, the sodium element was here is 13.70 and silicon is 37, but with an increase in electrolyte concentration, the weight of sodium as well as silicon elements get decreased. That indicates the formation of sodium and silicon solid ions. Because of the formation of these ions at the surface of the machined microchannel, the surface gets smooth. But in case of higher electrolyte concentration, what will happen? What will happen? Apart from smooth surface, there are some cracks. Why it is so? Because there is another side of the electrolyte concentration, another side of the electrolyte. When we increase the concentration of electrolyte, then there will be the thermal conductivity as well as the electric conductivity of the electrolyte also increased. Because of the increase of thermal conductivity of the electrolyte, when the discharge will take place underneath the two electrodes, then at that time it will evacuate the heat from the machining zone very quickly, because the thermal conductivity of the higher electrolyte concentration solution will be higher, and it will help to evacuate the heat from the machining zone very quickly. And because of high high electrical conductivity, the film formation will be high very quickly, and the discharge intensity will be high. Because of high density discharges, there will be quick liberation of in machining zone, there will be quick liberation of thermal energy, and there will be quick evacuation of thermal energy. Because of this quick liberation of thermal energy and quick evacuation of thermal energy from that machining zone, the material that comes under this effect will get contract, expand, will expand quickly and will contract quickly. Because of this, there will be some cracks. Because of there will be some stress, and because of these stresses, the surface will get cracked. By using these different electrolyte concentration, we can get the different kind of surfaces. And these are the conclusions. As I have told you in previous slides, by using the texture tools, we can generate the thin and stable gas film. Stability of gas film is very important factor in case of electrochemical discharge machining. By getting the stability in gas film, we can also get the repeatable machining condition. Because the gas film is an important component, the breakdown of that gas film, we can get the discharges. We can get the EDM action. Okay. So subsequently, the breakdown of this gas film, we can get the high frequency, low intensity discharges. And the second point, texture tool promotes uniform material movement underneath the active cross section of the two electrodes. As I have told you, as we have discussed in the previous slides, when I have showed you there are two cross section of the microchannels. But in case of texture tools, we can get the smooth microchannels. In terms of data, the material removal rate is increased by 19.27%. The width in terms of accuracy, the width overcut is reduced by approximately 122%, and the surface finish is improved near about 27%, and depth of penetration is increased 65%. And the most important thing is that the feature of microchannel, get the feature that we have to, that is our desire to get the rectangular shape, so that we can get by using this texture tools. The higher level of texture tools effectively penetrates the electrochemical discharge energy that results in the improved depth of penetration, while it preserves the machining accuracy. And as I have told you, the electrolyte concentrations are phenomenal over the surface quality, because as I have shown you, at lower concentration we can produce sprinkled patterns over the ground surface over the microchannel. These sprinkled patterns are very useful for micro mixing applications when we have to mix the two fluids in microfluidics. And further, these microchannels we can use for the microfluidic applications. And by using these texture tools, I have fabricated this microchannel device, microfluidic device. The cost of microfluidic device is near about 33,500, and what we have produced this same having the same feature in near about 100 rupees by using the ECDM process. And here I would like to acknowledge Dr. Akshay Dwivedi. He was my supervisor during my PhD at IIT Roorkee and Advanced Manufacturing Processes Lab, where I have accomplished this work. And I would like to thank Advanced Manufacturing Process Lab and Professor Akshay Dwivedi for the contribution to my PhD work. And thank you. Any question?
Thank you, Dr. Talochan. Nice you had. Thanks a lot for this much wonderful discussion and with us. Now I would like to request our participants so they can ask their queries, and some queries already written in the chat box. So I will read them for you, Dr. Talochan, so you can respond to them.
Okay, sir.
Yeah. One question is by he's asking what is the effect of auxiliary electrode tool material and distance between the workpiece and auxiliary electrode on machine performance.
Okay. First one, as I told you, when we place the electrolyte, and auxiliary electrode in a sequential manners, as I have told you in the slide, very first slides, then it will form the electrochemical cell circuit. Okay. So when we choose the different materials having different electrical conductivity. Okay. For example, in case of stainless steel or in case of graphite, both the materials having different electrical conductivity, then obviously the entire electrochemical circuit, the electrical characteristics of the entire electrochemical cell circuit will change. Because of this change, the film formation will be very fast in case of stainless steel because of high electrical conductivity. In case of graphite, the electrical conductivity will be low, then the film formation time will increase. So that's why the energy that we can get underneath the tool electrode will be higher in case of auxiliary electrode having higher electrical conductivity. So in this sense, we can explain the effect of auxiliary electrode material on machining performance of ECDM. In another case, when we increase the inter-electrode gap, basically the gap between tool electrode and auxiliary electrode, we can pronounce it as also the inter-electrode gap. When we increase the inter-electrode gap, then the inter-electrode resistance will also get increased. Because of the increase in inter-electrode resistance, the entire electrical characteristics, as we talk about the electrical characteristics of the electrochemical cell circuit, the electric energy will require more to perform the same task, and the film formation time will also get decreased. Because of this, the discharge energy that will be present, that we can get over the surface of tool electrode will be low. So in this way, we can say by increasing the inter-electrode resistance, the resistance will inter-electrode gap, the resistance will increase, and ultimately the material removal rate will get decreased. But when we decrease the inter-electrode resistance, it is basically there is an optimum value. In my case, I have found 20 mm. So when we increase that, the value of inter-electrode beyond 20 mm, then there will be some erratic discharges. Because of these erratic discharges, the machined feature, the shape of the machined feature will get deteriorate. So that's why there is some optimum value, and that is near about 20 mm.
Okay. Thank you, Dr. Talochan, for the clarification over the query. The next query by Praveen, he is asking that is it possible to machine diamond plate with ECDM process?
Sorry. I'm not getting the point.
Is it possible to machine diamond plate using this
Okay.
ECDM?
Okay. Yes, we can machine any kind of material by using the ECDM process. But in that particular case, you have to you have to follow some specific instructions, and you have to follow some specific. There is some specific limitations. Here I want to quote some example. In case of metal matrix composite, you can directly apply the metal matrix composite. Then you have to make some modification in the basic electrochemical cell circuit configuration. Then you can machine. Even you can machine any kind of material by using ECDM process, but you have to follow some basic instructions in terms of tool covering, in terms of workpiece covering, and other things.
Okay, thank you. Can we merge ECM and EDG, means electro discharge grinding, I think.
Sorry, sir. We can match.
Can we merge ECM and EDG, electro discharge grinding?
Sir, why not we can merge both the processes?
Yeah. Obviously.
Here, there is one article in machine tool and manufacture. We will see the integration of both the processes with grinding action.
Definitely, we can make the common of tool, so it can perform the ECM aspect as well as the grinding function also, I think.
Yes, sir. Yes.
Ranjit is asking, what is the benefit of ECDM over individual use of EDM and ECM?
Yes, in case of ECM and EDM, we can't machine non-conductive materials. They are bounded. Both the processes are bounded to machine conductive materials.
Yeah,
But by ECDM, you can machine either conductive, either reflective, either polymers, any kind of surface.
Okay. Another query by Neeraj. He's asking, what are the major influencing factors to be taken care of during extremely brittle material in ECDM?
Yes, sir. There is no need to take. Yes, sir. There is no need to take care special to follow special instruction, but you have to control the parameters. In case of brittle materials, then we increase the applied voltage beyond some certain limit, and at that time, because of the high intensity inconsistent discharges, the material get fractured because of their brittleness. Because of this, we have to take care about only energy controlling parameters, and that may be your applied voltage and electrolyte concentration. These two are important parameters.
Okay. I think you have conveyed so many queries, Dr. Talosan. So it was a very great and wonderful discussion and talk you had. And we really enjoyed. I hope our participants, as they are just responding in the chat box, it was really amazing and awesome discussion and talk. Thanks a lot, Dr. Tolosan, for being with us.
Thank you, sir. Thank you for inviting me. Thank you, sir.
Thank you. Thanks a lot. So participants, for the next talk, we will meet at 2:30. Okay, so our next talk will be there. Okay, so it's a session break, so we will meet at 2:30. Thank you.
sir?
Yes, yes. I can hear you clearly. Can you hear me clearly?
Yes, sir. Yes, sir.
Oh.
Perfectly. So in the meantime, as our participants are just joining in a while,
Yeah,
so you can also just check your slides by.
yeah, you can take your own time, or you want to check me. So yesterday also,
Uh,
I did the same. Just I need to do present. Yeah, let me put you
yes.
like this. 1 minute.
Yes, sir.
Yeah.
Please.
Can you present now? Just the entire screen. Allow. So can you see my screen now?
Yes, sir. It is coming perfectly, sir.
Can you see? Yes.
Yes, sir. It is coming.
Yes. Thank you. So once all the people are ready, then I will present. So I'm stopping presenting. So once the people are,
Yes, sir.
yeah.
Definitely, sir. Then I will. Yeah. Please.
Okay.
Good afternoon. I welcome you all in the post-lunch session of this session.
Voice is
With
Ravi sir, I think your voice is not coming clearly. I think you are not audible. There is connection problem.
yeah, let him complete.
not
So there is a disconnectivity from Pratap. Pratap, I think you need to check. Your voice also not clear to me.
okay. Let me check, sir, please.
Yeah, now it is audible.
Is it audible now, sir?
Yeah, audible. So am I audible?
Yes, sir. Yes, sir.
Yes, sir. You are audible.
Okay.
Before requesting about expert to deliver his talk, I would like to just share some brief about him. Dr. Ravi Shankar is currently an associate professor in the Department of Mechanical Engineering at IIT Tirupati. He did his masters and doctorates from IIT Kanpur. his research interests related with the micro nano manufacturing, sustainable manufacturing, precision 3D printing, online monitoring, biomanufacturing, coating, tribology, etc. His lab also involves in the development of lab scale innovations to commercial manufacturing products. It means paper to product technologies. He has published over 50 plus articles in internationally reputed journals, 80 international conferences, 6 patents he owned, 2 edited books, and 10 plus book chapters. The knowledge transfer of his patents is already transferred to India's leading research laboratory, such as CMTI Bangalore. Presently, his lab possesses with various funding from BARC, DST, DRDL, BIRAC, SUB, etc., of about 30 million rupees as a principal investigator and 600 million rupees as co-investigator. He has guided 5 PhD students, and currently there are 8 students working PhD under his supervision. He is also a reviewer of very reputed and international journals with the publishers like Elsevier, ACS, Springer, Wiley, Indus Science, Sage, etc. He is also the editorial board member of IMACI Journal of Micro Manufacturing and guest editor of International Journal of Precision Technology. He has Professor M. Ravi Shankar is also recipient various prestigious awards such as Institution of Engineer India Young Engineer Award in 2015 in Production Engineering, Indian Society of Advancement in Materials and Process Engineering 2011, finalist of Indian National Academy of Engineering Young Engineer Award in 2014. It was some brief about Professor M. Ravi Shankar, and list is so long. So due to the time constraint, I need myself to stop over here and request Professor M. Ravi Shankar to please share his research experiences and enlighten our participant with your views, sir. Sir, please, we welcome you, sir. Please.
Yeah, thank you. Am I audible, I guess?
Yes, sir, please.
Yeah.
You are audible.
So, thank you. I'm just presenting my screen. So once the screen is okay, then do let me know so that I will start. Yeah.
Okay, sir.
So I think it's now fine.
Yes, sir. Yes, sir.
Yeah. So they put in a screen mode. So the screen is okay to all the people?
Definitely, sir.
Yeah. So thank you, Professor Ravi Pratap Singh and NIT Jalandhar for giving me the opportunity to showcase what we do and what we collaborate and other things. So, okay. So,
Okay.
let me talk about, because when I saw, basically I work mostly or extensively into abrasive flow finishing techniques, because almost all more than 25 journals are there. However, so 2 faculty already taught about that, Professor Ravindra Singh Walia and Professor Pradeep Kumar, who are well known to me also. Okay, so I am talking about some other things. Wherever you have doubts, you just keep till the end, and you can ask me at the end. Okay, so regarding IIT Tirupati, many of you may know, and those people who don't know, IIT Tirupati comes under the 3 GIITs, third generation IITs, along with other IITs like IIT Goa, Bhilai, Jammu, Palakkad, and Goa, Dharwad, and other things. Currently, we have 5 specializations, and we have started in 2014, and currently we have our own targets, and as per the Indian MHRD is concerned, we are the number 1 position among the third generation IITs. So this is what we came to know, but I don't know exactly. So regarding the Department of mechanical engineering or the various departments that we have currently is chemical engineering is the additional one, which is the youngest one. So we have civil, computer science, electrical and mechanical, which are core branches which started earlier. And recently we added chemical engineering 2 years back, and we have other social sciences, chemistry, physics, maths, and other two departments which we are going to get is materials science and metallurgy department and the school of design. Those people who works are, because some of the people who may be watching may be experts also. So these are the areas which we are expected to start at 2019, but because of practical issues, which we may start in 2021. So I just want to say acknowledgement to Professor V.K. Jain, because some of the slides which I borrowed from Professor V.K. Jain as a supervisor to me, so he kindly shared some of the slides. Okay, so I am very thankful for my supervisor, Professor V.K. Jain. Regarding my research, the core research area that I do is micro machining and nano finishing, which is a big group of students work in this area, and sustainability in manufacturing, where we do. I just brief you about what we do at IIT Tirupati, especially in my research group. And we have two groups recently started few years back. That is smart manufacturing, which is CPS based, cyber physical system based, and industry 4.0, and additive manufacturing group. So additive manufacturing comprises of composites, polymers, composites, metals and ceramics, and metal matrix composites and other things. So we touch most of the areas. I may not present you much things in this area because it is still most of the things are going on. And bio materials and manufacturing group, which we have extensively. Three groups we have enormous work done, that is micro machining and nano finishing group, sustainable manufacturing group, and bio materials and manufacturing group. Okay, these are the three groups which we have extensively done. So coming to the initial, which is bread and butter for our particular laboratory, that is called micro machining and nano finishing laboratory. So our the group approximately 4 to 5 PhD students and approximately 10 masters has already worked in this area. So including micro machining of shape memory alloys, micro machining of advanced high temperature materials, biomaterials for drug eluting stents and other things. So we also worked for the nuclear back-end fuel cycle for the Baba Atomic Research Center, where high aspect ratio micro holes are drilled and polished, and microfluidic channels as the thermal people always require, because mechanical engineering comprises of thermal design and manufacturing. So we always support the thermal division with the microfluidic channels and other things. We also work on fuel injector nozzles and so on, coatings and other things. Regarding the sustainable manufacturing, so sustainable manufacturing, we work in two aspects. One is development of advanced cutting tool materials and making the cutting tools, and another one is cutting fluids. So whatever you are seeing is a cutting fluid. Whenever a mineral oil based cutting fluid fall on a machining region, a lot of smoke and other things will come. So these will go fall on your face or on your hand. That causes a lot of problems like contact dermatitis, chlorinac, and if you people breathe in, because since we are the manufacturing guys, a lot of our students and we keep working on our laboratories, and this causes a lot of problems like hair follicles, thyroid cancer, asthma. Asthma is one of the common problems that most of the people who uses mineral oil based, and mild bronchitis and other things. That's why we develop our own cutting fluids without compromising the lubrication properties and cooling properties. So we develop on hybrid cutting fluids also. So the other one, what we do in the micro machining is biomicro machining, where the concept of advanced manufacturing comes here. So in a conventional machining process where your cutting tool should be much harder than your workpiece, that is what the conventional thing says. But advanced manufacturing like EDM and other things says you need not to be need not to be a hard compared to your workpiece material, where you can cut a hard material with the conductivity if it is conductive, so you can cut by copper wire also or a copper tool. So what we did here is we stepped further and we demonstrated that machining of metals by bioorganisms, that is called biomanufacturing or biomicromachining, where we did used Acidothiobacillus faraccidens columns. So what we do is we get the Acidothiobacillus faraccidens, which is in a standard format from the biological laboratories of India. Then we do the culturing, because this is a very important. How do you culture? At the same time, what you have to feed and how you have to feed, and what will be the age, at what age those are have the maximum efficiency and other things. A lot of studies are gone into this one, and once you make your sample by the photolithography and the exposed area, if you see a micro nozzle, the exposed area you have to expose, and other thing you have to cover with the material, and then you have to place inside the Acidothiobacillus faraccidens populated columns. Then it will take away the materials by the biochemical actions, and you can see here a micro mixture, how the micro mixture is generated, and the most advantage compared to some of the advanced machining processes. For example, you can develop this by electrical discharge micromachining, laser micromachining, and other processes. But the metallurgical problems will be a big challenge there. So microstructure may not be the same as a parent material. So this particular process, whenever you are thinking about a biological applications, so you don't have much change or negligible change will be there with respect to your parent material metallurgical structures. So the morphology, you can see it's very better, and metallurgy also not a big change as compared to your advanced high temperature processes like laser and EDM. So we also work on bulletproof materials for Indian Army, because one of our student who works in our laboratory is Major Sanjeev Kumar Sahu. When he joined, he was a major, and now he is a lieutenant colonel. And he is working now currently at Jammu Kashmir. So he is our external student, and we understood by considering what the current state of art materials that Indian Army is procuring, and he is working because he himself is a major. So for him, there is no much problem in addressing all these things. So you have to understand the basics of how the penetration has to be taken and how we can prevent the penetration. That is the most important thing. How do we deform? So first few layers, what you require. Next few layers, what you require. This particular material, we have to do the simulations with respect to material properties. Then we do fabricate. So you can see here, which is the army people place on their chest. This is a standard and advanced version of which contains nearly 90 micron layers of materials, which are advanced materials that are coated with the nano materials. Okay, so these are one of the state of art, and we also work on ballistic applications also. See, these structures, once you develop the structures, you can develop for the vehicles also. So that is what we are checking. This particular thing he has done in his masters. Now he is doing some of the advanced versions for his PhD. So as I said, we are also working on advanced manufacturing, which is also additive manufacturing. So additive manufacturing, some people, they say it is a part of advanced manufacturing. So it's okay. So what the thing that we are going to do here is, if you see, the primary thing is whenever I visited some of the institutions and laboratories, 3D printing they are using for many applications, and one has to understand when they have to use additive manufacturing. Additive manufacturing is not suitable for all type of applications. Some of the type of applications, normal machining is much better. and economical. So some of the applications where you require is the satellite applications, biomedical applications, and other things. If you see here, the satellite applications original, it is having a 16 parts and which is riveted at various sections. But if whenever you do the topological optimization and you redesign, it goes to 940 grams. That means that every gram in a satellite is considerable amount. That's why at the same time, the weight loss is one thing and it is a single component. So efficiency will be much better and this particular component will be used as you can see in the satellite circular position. Okay, these are the biggest components. And at the same time, if you see, these are some of the components may be used in drilling rig. At the same time, these are the components that are used in some of the defense applications also, because we are unable to show those realistic things. That's why we are showing for the drilling rigs. So what is the basic problem here is these are having a multiple holes. It is very easy for anybody to do the drilling of multiple holes. But the problem, if you see the three-dimensional transparent model at the bottom, these are all to be connected for the basic functionality. So the connection may be a perpendicular direction or at certain angles. That connections or interconnections is much difficult, and people normally will take approximately 1 month to 2 months of time to fabricate this one. At the same time, the cost escalates enormously up because of the interconnecting these layers. So you can redesign and you can make it in a good functional component. As you can see here, so you can do a 3D printing of this particular structure and maintaining the functionality. What you can see here is the biggest advantage is you can reduce the weight by 90% and the cost also you can reduce. Okay, 14.6 is the original and it is reduced to 1.3 kg. So you can see a great improvement in the materials saving as well as manufacturing time and cost also. So these are some of the applications where you have to think about additive manufacturing. So whenever you see among the conventional and advanced versions of additive manufacturing, if you take internal features of hydraulic manifold, this is what a conventional guy in additive manufacturing will do, which weighs around 5.1 kg. On functional surface is 823 centimeter cube. But maintaining the functionality, we can reduce the weight and other things. So there is a concept called lattice structures. So these lattice structures, if you can see here in a cross-sectional section, this is perfectly a solid one. Here you have a lattice structure. So weight is reduced to 1.9 kgs and functional surface has increased enormously. So with the same loading capacity and other things, people can go for it. This is enormously, many people are doing a lot of research on lattice structures, different lattice structures. So not only this, we also work on coatings, macro coatings, micro coatings, and DED, that is called direct energy deposition, direct metal deposition. We also work on WAM, wire arc additive manufacturing processes, and WAM, twin wire arc additive manufacturing, and others. We have so future in a big spectrum of additive manufacturing, where currently we have some of the equipments and some of the equipments we are going to get. So laser cladding we have RF sputtering based cladding, we have WAM, we have TWAM, we have, and metal we are going to get it, and DED and other things we are about to reach. So we also work on smart manufacturing, as other people might have talked on about abrasive flow finishing process. We have developed a commercial scale abrasive flow finishing process with a human interfacing based and other things. As you can see, IIT Tirupati, we have developed a abrasive flow finishing process with a completely automated system. Only just you need to put the component in the picture, and you need to feed it to the system. So completely it is, yeah, I cannot say it is complete 99% or something, but some of the human interventions are required. So we are working on how to upgrade to a industry 4.0 based smart abrasive flow finishing system. So what I mean to say is we not only publish the papers, we convert, as Dr. Ravi Pratap Singh was saying, that our primary focus is also on development of paper to product technologies. So mere papers may not be a right choice for us. So we also work on development of commercial scale machines, and we develop and we submit or we hand over to the research laboratories also. We, as he was saying in my introduction, we have given to CMTI Bangalore, which the image you can see at the end of this presentation. So the other area where we extensively work is biomanufacturing, where we do coat using lasers, we do coat by PVD techniques and other PVD, as you know, physical vapor deposition techniques and other things. So initially we started this with the laser micro manufacturing or laser cladding systems, and where you can see the cladding structure. Then you do the cross-sectional analysis, then you can find how the elemental mapping. You can see here titanium, or the green particles are the titanium. Then we have done a functionally graded coatings on the top, where you can see pink ones and red ones. Pink ones are calcium, and another one is a phosphate based biomaterials. And if you can vary your input conditions with respect to the materials that are placed, you can generate different textures, because whenever you want a porous structure, you can have a porous structure. Whenever you want a dendritic or a lamellar structure, you can have a lamellar structure. Then otherwise you can have a solid structures also. But preferably for bio applications, you should have always a porous in terms of dendritic or in terms of lamellar, in terms of any other porous is required, because your cells has to adhere to the surfaces. This is most important, because you cannot build a house without any basement. So you need to grow the cells. That means that you need to have some porous nature where this can extend their roots so that they can hold firmly on the surfaces. We also work on biocompatibility test. So once we coat, then what we do is we do keep on simulated body fluids. Once you keep on simulated body fluids, it develops the basic apatite layers. So this is apatite layer is the one that develops by the body fluid, that is called simulated body fluid in vitro condition, and hydroxyapatite is what the material that we coat basically. So basically problem for a mechanical engineer is tribological applications. As I said, if at all cell has to grow, you need to have porous structure. But whenever you want to coat the surface, at the time also you require some texturing. Otherwise, the tribological aspects or delamination of the coating is a predominant phenomenon, because whenever you have taken a titanium surface, which is a bioinert material, and on a flat surface or a polished surface, if you do coating, what will happen is this coating is a bioceramic and your workpiece material is a ductile material, which is an alloy, titanium based alloy. There is a heavy chance that the delamination will be there. That's why you need to develop some texturing. So the texturing can be hydrophilic or super hydrophilic surfaces, because at this particular junction we want a hydrophilic surface or lipophilic surfaces, as you can see in the scheme. So not only the interfacing or the overlapping that we do, we also understand what is the microstructure at different zones, and we also understand these particular things with respect to 3D graphs and EDS, energy spectroscopies. Then once we do the texturing, then we do the coating. On top of the coating, we do again biocompatibility test and tribological test and other things. You can see the beautiful So whatever the black that you are seeing on the screen is the coating, and whatever you are seeing a beautiful flower structures, those are nothing but the apatite layer. So this is developed between the simulated body fluid and between the uh, surface that is coated. That's why this particular thing shows that this particular material is biocompatible, and you can go ahead for the cell culture analysis. Then whatever you are, this is whatever you have seen on a titanium surface, but the basic drawback here is once you put inside a human, you need to take out. For example, if you are putting a coated titanium surface or a titanium implant inside a human, like a bone plate or bone screw or whatever thing, what you require is you need to take out after a few years or 1 year, after 1 year or something when the healing is completed. So the patient required secondary operations. So in order to avoid secondary operations, because why you have to avoid? Assume that a middle class person is going to have this particular thing in his body. So primary operation, assume that it is costing 1 lakh rupee. The secondary operation to take out, it will also cost approximately 60% or 50%. So again, it takes 50 to 60,000 rupees for the secondary operation. So we developed biodegradable polymers along with the chemical engineering departments, and we work very closely with the Center for Sustainable Polymers, and where we have synthesized lactic acid monomers, then we do polymerize, depend on the polymerization, and we manipulate as per our requirement the molecular weight and other things. So once you make this polylactic acid, which is a after doing the polymerization of lactic acid, then we do use bioglass, calcium phosphate, different varieties of calcium phosphate materials like hydroxyapatite and nanohydroxyapatite, bioglass, bioactive glass. Many varieties are there. There is a slight differences are there. So people, because of the time, then we developed basic structures like strands, because you require the strands. Normally, all the 3D printing systems require the strands. So if at all I want to 3D print a biodegradable implant, so I need to make a strands. We have made a strands. We have made the covers, whatever the things that whenever the brain relevant or head relevant injuries are there, this has to be kept on the top of that. Okay, so then once we develop the recipe and basic structures, we have developed the cancellous screws, cortical screws, Steinmann pins, platelets, staples, and other things with respect to polylactic acid and nanohydroxyapatite and other things. These are the patented technologies by us, and these are developed and these are the tested also. The other technologies is hydrogels. So what are the thing is that whenever people talk about the 3D printing and other things, 3D printing has its own drawbacks because the surface roughness or the features that it develops is very big. So if at all I want a nano features and other things which we cannot develop, that's why we have developed thermosensitive injectable magnetic scaffolds, which is a high intense research oriented technologies, and this contains a lot of polyethylene glycol based hydroxyapatite and proteins. This is a big study that went on, and we did the cell culture on top of it. MG63 is one of the osteoblast cells, because as I said, these are the technologies goes for the bone applications. Since we have knowledge on thermosensitive gels, since we have knowledge on cell culture and how to do so, then currently we are also developing the bioinks. Bioinks is nothing but cellular structures that are embedded in polymer networks. So these polymer networks are gels which we have that knowledge. Then we take the stem cells or required cells. Then we also know, being a mechanical engineer, we can do the modeling of any feature, and we can do, this is called bio 3D printing. We also work on this area. So this is about what we do at IIT Tirupati and IIT Guwahati. As I said I forgot to inform you that I worked at IIT Guwahati for 7 years and moved 1.5 years back to IIT Tirupati. So we have two research groups. One research group is working at IIT Guwahati and another research group working at IIT Tirupati. We have around 14 to 15 PhD students and 10 master students and 5 bachelor students are working on this one. So coming to nano finishing processes, I'm exclusively talking about the magnetic field based because abrasive finishing based is taught by other people. However, there is a requirement to understand abrasive flow finishing also. That's why I put few slides on abrasive flow finishing also in the present study. Okay, so micro nano finishing process, we have a traditional and advanced finishing process. In traditional, we have grinding, lapping and honing processes are there. However, there's a problem because these are mostly solid tool based except lapping process. So there is a shape constraint and size constraint with this traditional finishing processes, and that's why people move at advanced finishing process. The first and foremost and very famous process is abrasive flow finishing process, which you might have already gone through. Magnetic abrasive finishing process, magnetorheological finishing process, and magnetorheological abrasive flow finishing process. And one of the advanced and hybrid, since this particular course is on hybrid, so I end up explaining about one of the hybrid advanced finishing process that is called chemomechanical magnetorheological finishing process. So these are some of the varieties which we are going to talk about. Except MFP, magnetic float polishing, we are talking about most of the varieties. Okay, so we talk about MAF, which is magnetic abrasive finishing, abrasive flow machining. Some people call it as abrasive flow machining, some people call it as abrasive flow finishing process. MRAFF, MRF and CMP, we just go to the higher version of CMMRF, that is called chemomechanical magnetorheological finishing, and we don't teach in this particular session about MFP process. So the first one which we are going to talk about is magnetic abrasive finishing process. In this area we have 2 publications along with Professor V.K. Jain, the schematic diagram. So if at all you want to generate on a flat surface or a cylindrical surface, one thing is sure that basically the magnetic based abrasive finishing processes are confined to the simple to partial complex surfaces. These are not confined to very complex surfaces such as abrasive flow finishing. But that's why, as you can see here, MAF process can be used for the flat surfaces where you have a flexible magnetic abrasive brush. What is flexible magnetic abrasive brush? Flexible magnetic abrasive brush consists of abrasive particles and CIP particles, carbonyl iron particles, and some of the oils to hold firmly both of the things. And it can also used for the cylindrical surfaces and other things. Okay, so there is a bonded and unbonded abrasives which you might have come across in grinding process. So in this one, what you are going to see is abrasive particles where along with the ferromagnetic and other things. You can see here, this is a setup that developed, this is a setup that is developed at IIT Kanpur by Professor D.K. Singh and Professor V.K. Jain group. So if you take this particular finishing zone, you can see here, normally this is your magnetic region and this is your workpiece. Normally there are 2 types of workpieces that can be polished. One is magnetic and another one is non-magnetic. However, finishing will be much better on a non-magnetic workpiece because if it is a magnetic workpiece, there is a chance of firmly bonding rather than a relative motion. That is one of the problems. However, you can use this particular process for magnetic also. So the only thing is that you have to simulate by Maxwell software how the magnetic field force of lines are traveling. That you have to understand. You can see here the initial surface, then after the MAF in the initial stages, then again, it is achieving 0.11, that is 11 nanometers is the surface. And the best surface roughness also you can, here is 110 nanometers, so best surface you can achieve up to 40 nanometers. This particular process also can be extended to deburring. So basically in conventional machining processes or conventional micro machining processes, okay, so like micro drilling or other processes, you can see these type of chips on the backside of the workpiece. These chips can be removed by various processes. However, if at all I want to do perfectly, so one of the process that you can utilize is MAF process. Okay, how we can do the deburring action? You can see here. This is the surfaces that are generated by EDM process or laser beam machining process. These are much harder surfaces because maybe a carbide leakage. If at all you are using a mineral oil based or a carbon based dielectric fluids, so whenever you do the micro drilling using micro EDM process, so you get a very hard bars. These are to be polished perfectly. For that purpose, you can use magnetic abrasive finishing. You can see the same thing how the birds that are extended. In other terms, you can say that if at all I want to remove the recast layer and other things which is extended towards the lateral direction, you can do by MAF process. Next, move on to the another process that is called the magnetorheological abrasive flow finishing process. As you can see here, this is where you require the knowledge of abrasive flow finishing process. Okay, so if you can see here, this has a flexibility of MRF process. It has a flexibility of AFM or abrasive flow finishing process. Combinedly, it is called abrasive flow finishing process, or it is combinedly it is as magnetorheological abrasive flow finishing process. That's why you require the knowledge of MRF process as well as abrasive flow finishing process before you enter into the magnetorheological finishing process. Okay, this particular slide will come after abrasive flow finishing process and MRF process also. So just at the time I will explain in a other way what is written at the bottom. So abrasive flow finishing process. This is the process. You don't use the magnetic field. However, you use the polymer rheological abrasive medium. And this has three main elements. One is machine tool itself. Second one is tooling. Tooling is to hold the workpiece firmly and to guide the medium across the surface to be polished. And the third and most important is medium. So the technology here is how to develop a sophisticated machine tools nowadays, smart machines and smart tools also, because flexible tools are available. And most important thing among these three is the medium, how we can develop a viscoelastic semi-solid mediums. So why viscoelastic medium and other things people might have already talked to you. So we have done for finishing of other things. The basic properties of this particular medium is flows like a fluid, jumps like an elastic ball, and breaks like a plastic piece and other things. What I mean to say is that the same medium has a flowing characteristics and elastic characteristics and plastic characteristics. So it has a unique characteristics. That's why one has to understand the rheological aspect. The rheology is nothing but the science of flow and deformation. So we extensively did on steady state rheology and dynamic rheology using the standard rheometers, MCR 302, MCR 502, MCR 102 and other things. And we have come across various rheological characterizations of this particular medium, and later it is polished by various techniques. This is also polished by abrasive flow finishing techniques. This is also polished by various other techniques also. As you can see here, the knee implant is polished at CMTI Bangalore by our own technology. This is also can be used or extended for heart valves and hip implants, and the hip stem also you can do, hip head also you can do. These are the technologies that developed with our own patented technology at various institutes like IIT Kanpur and CMTI and IIT Guwahati. So this particular technology not only do for big or macro surfaces, it also can be extended towards micro surfaces. So for example, fuel injector nozzles, we can do the precise polishing so that the fuel injection can be approximately optimum or as per the desired. And recently we received one project from BIRAC, Biotechnology Initiation Grant, on nano polishing of cardiovascular stents. What we did here in this particular project is we did the laser micromachining of nitinol based stents, then we did the polishing, and now we are going to check for the biological applications, extensive biological applications for various in vitro conditions and in vivo conditions. It is an enormous study that is put on this one. So the second version is a magnetorheological finishing process. Whenever we talk about magnetorheological finishing process, so this is a liquid. As you can see here, the fluid is extruded through a rotating wheel. As if you can see in a schematic diagram, the pump is there, nozzle is there, a liquid is falling here, and you have an electromagnet here. Because of the electromagnet, this will become a flexible ribbon that you can see on the original image. You can see perfectly a ribbon. Here at the exit, it is a liquid. Because of the electromagnet or a permanent magnet which is residing inside, it is becoming a flexible. Depend on the magnetic field intensity inside this ribbon strength, or in your grinding terms, the grade of a grinding wheel will be decided. So whether it is a soft grade or whether it is a hard grade, these are all will be decided by the magnetic field intensity inside. Okay, so you can see here in a schematic in a big way where the fluid delivery is there here. Once the fluid delivery is there, you have a magnet, a pair of, you can have a permanent magnet or you can have a electromagnet also. Advantage of electromagnet is you can control the magnetic field. However, in a permanent magnet, you can have only a fixed value of magnetic field intensity. That's why people always go for an electromagnet, so that they can assume that today I want to polish one surface where initial surface is this and your final surface requirement is this. Tomorrow your requirement will change. For that purpose, what the people do normally is they change the they change the magnetic field by using electromagnets. That's why. And then there will be a suction pump. That suction, then again it will be sent or recirculated to the finishing process. This is a setup that developed at IIT Kanpur by Professor V.K. Jain and its group. So on a magnetorheological polishing, there is a disc, and you can see here there is a silicon mirror surface is there. So zoomed version of this, whatever you can see here, this particular is a fixture. Whatever you are seeing a transparent one, you don't think that that is a workpiece. That the center there is a circular workpiece is there, that is a silicon workpiece. So you can have two varieties of magnetorheological fluids. One is water based, another one is oil based. Whenever you go to the silicon, normally people prefer water based because of its chemical interactions between silicon and water. That's why people normally uses water based MR fluid, that is magnetorheological fluids. You can see here, so these are the commercial spectrum of MRF process, where you can see okay, excuse me. You can do the polishing of multiple workpieces in a go, and big workpieces, and you can your flexible grinding wheel has different motions to do different varieties of workpieces, like sapphire polishing and inclined concave and convex polishing, lightweight silicon carbide mirrors polishing, and other things. This Silicon mirrors is one of the biggest challenge. Those people who want to take, they can take. So there are two big challenges. MRF process is very suitable for polishing of silicon carbide mirrors that are used extensively in satellites applications and many defense applications also. Still, India, we are struggling to do a big components polishing. As you can see, the mirrors requirement is more than 1 meter, and each and every nook and corner of the surface should be uniformly polished to a sub Armstrong level, not the nano surface finish. That is the biggest challenge. So material removal mechanism normally you can see on a surfaces. So if you see the material removal mechanism, there is abrasive particles, and if you see, there is a liquid is flowing, and once a magnetic field is there. So the pink ones are CIP particles, and abrasive particles are the purple ones. When the magnetic field is applied, magnetic field of force of lines will travel from north to south. There will be a, you can see here, there is a magnetic field which is in red color. So the magnetic chains will form, and these chains will hold the abrasive particles which are indicated in purple color. So the finishing will be done by these purple color particles, but how smoothly these are held will be decided by the pink abrasive particles. Whether I want to hold with low grade or high grade, that flexibility you can control by electromagnetic field intensity. Okay, so you can see here there is a normally strategic mechanism, because here it is a simple normal shearing operation only. So if you consider as a triangular surface, when there is a magnetic field of lines intensity, there will be a radial force and axial force. Because of this radial force and axial force, the polishing will takes place. This is a same mechanism that is in abrasive flow finishing, grinding, and other things. Now you can see how the surface finish is achieved. So original initial surface, as you can see, it is 1260 nanometers, that is 1.26 micrometers. The final surface roughness which we achieved, V means Professor V.K. Jain's group achieved, is 12 nanometers. How smooth the surface is. So how the undulations are removed by the MRF process. So that is evident from the mirror surface finish. This is the initial blank surface on a silicon blank that is received. On top of it, the three-dimensional surface profile meter is checked, and it is 1.26 micrometers. Then after finishing with the MRF process, you can see it is 10 nanometers. Whatever you have seen in the previous slide is a 12 nanometers. Okay, so approximately how the mirror image is clearly seen on a silicon substrate after polishing by MRF process. There is another variant developed by Professor Sunil Jha at IIT Delhi, that is called ball end MRF process, that is called BE-MRF process. The flexibility here is, if at all I want to do the polishing of complex features, so you need to make a pointed flexible magnetic abrasive brush. So that is achieved by another technique which is called BE-MRF technique. So here MRF finishing tool is there, and you can see the copper coils. Normally there is electromagnet which heats up, so it has to be controlled, or its temperature is controlled. For that one, these copper coils are there, where inside the fluid flows and cools the surface. You can see here the demonstration of flat surface, concave surface, convex surface, and tapered surface, and other surfaces are explained by the researchers. So this is another variation where you can see the same concept. However, it is used for finishing of knee implants. As you can see here, whenever you put a droplet on top of the knee implant, and whenever you approach the ball end, so whenever it approaches, jumps and stick to the magnetic field and forms a fibril structure that is nothing but the magnetic chains. These chains consist of the abrasive particles, and these chains are held by the abrasives are held by this magnetic field chains. Okay, so then the polishing is done on a knee implant, as you can see here. So knee implant surface finish is achieved. An initial surface where you can see nothing is visible. IIT Kanpur, this is a particular project where I was worked as a scientist in this one, IIT and Bark. So you can see here after some finishing cycles and after optimum finishing, you can see these surfaces. The basic drawback here is that processing time is very high. This particular component is finished approximately few days. I am telling about only working hours. Don't consider night time or something. So working hours, it is finished for a few days. So in a manufacturing production line, if your finishing process is so good and if your production time is very high, there is a problem. So in manufacturing, time is money. So people don't want it. It has to be done at very, very low production times. That means that production rate should be high. So another one is non-uniform because different curvatures are there. That's why here you can see here that's MRAF process which we have seen. Now we understood what is abrasive flow finishing process, what is MRF process. Combination of this is nothing but magnetorheological finishing process, where we can use the advantage of abrasive flow finishing because where you can flow to the nook and corner and you can control the finishing forces by magnetic force of lines or magnetic field intensity. As you can see, the chains where C particles are small ones and abrasive particle is this. Whenever you apply a magnetic field of lines in a MRF process, what will happen here is your CIP particles, carbonyl iron particles. Carbonyl iron particles means purest form of iron particles will form chains, and these chains hold the abrasive particles. As you can see here in this one, your chains are there and your abrasive particles are held, and these are reciprocated by similar setup such as abrasive flow finishing, but you have a north and south poles on both the sides. So whenever you have a north and south poles, magnetic field of lines will transfer from north to south pole. So there will be a chains formation from north to south pole, and hydraulic power pack is pushed from perpendicular to it. So what will happen here is you can see the finishing action by this particular MRAF process on a silicon nitride surface. Silicon nitride is much harder workpiece. So the people worked on the stainless steel and other workpieces also. However, there are some problems. What are the problems? The problems is it's also having non-uniform and difficult to provide a uniform magnetic field. That's why people move towards rotational magnetorheological finishing, abrasive finishing process, where rotational motion is provided to the workpiece fixture, or rotational motion can be given to the magnetic field. Okay, so what in this particular thing is done is at IIT Kanpur, Professor V.K. Jain and Professor Manas Das group, they have used the permanent magnets and they have rotated that in the magnetic field. When they rotated the magnetic field, so the uniform finishing can be achieved on a cylindrical surfaces. So this particular thing is done. You can see here initial surface is normally this surface is if at all I want to do a initial surface with a uniform roughness value, normally the people prefer to go for boring operation. That's why you can see the boring marks here, which is like a turning marks, and then after that finishing is taken place, which is 16 nanometers. And because of the rotational effect, you can also get cross-hatch patterns and other things. This is very good for the cylinder linearts and other things. This technology is further extended to the knee implant polishing, where rotational effect is there, magnetic field is there, and this can be done by abrasive flow finishing process also. So combination of magnetological finishing or magnetic intensity and abrasive flow finishing and rotation gives the better finishing. That is what the authors claim. As this particular course is on hybrid processes, the one of the process that I am going to explain you is chemomechanical magnetorheological finishing process. People know what is CMP, that is chemomechanical planarization or chemomechanical polishing. Chemomechanical polishing is one of the advanced techniques of the polishing where you have a polyurethane foam along with the abrasive gels and other things, and you can have the plate on which the workpiece can be mounted. Okay, so that it can do the polishing. However, in this particular thing is what is the thing is limitations of CMP, just we understand. Here, it is not able to planarize with the constant finishing throughout the workpiece surface. It does not have flexibility regarding the workpiece, regarding the shape and size. Normally, CMP is good for the plane surfaces. That's why here it is modified. So, chemomechanical polishing is very good polishing process where you can achieve sub-nanometers, and magnetological finishing can control the finishing process. These two advantages can be considered. That is called a chemomechanical magnetological finishing process. So where magnetic field assisted polishing pad instead of conventional polishing pad, and flexible polishing pad removes the shape and limitations of the workpiece also. So laboratory version, the people you can also develop at liver laboratories, this particular process. Only thing is that you should know how to play with the chemicals, how to play with your magnetic field, how to play with different compositions of MR fluid. That is the only requirement regarding setup. Setup is not very complicated. Regarding simple flat surfaces is concerned, you can have this particular, and you can have a flexible abrasive brush that consists of chemicals and magnetological fluids. So these magnetological fluids, whenever try to polish, the basic mechanism here is that main MRF, how it works is, so we always take the chemicals that are suitable to soft the workpiece. For example, silicon is the substrate and water is our chemical in this particular aspect. What will happen? Water makes the silicon much softer. Okay, how? And then the abrasives makes it polishing. So, for example, I don't know whether how you understood. I have the workpiece of hardness H1. So the parent material hardness is H1. So I have an abrasive particle H2. Okay, hardness is H2. Whenever I put some chemical on the workpiece surface is become a passive layer. Okay, up to some nanometers or micrometers. That is H3. My H3 is less than H2, but H2 is less than H1. That means, I don't know whether you can understood or not. So in that circumstances, my workpiece is harder than abrasive particles. Whenever I am putting a chemical, the top layer which is passivating becomes less harder than abrasive particles. That means my H1 is greater than H2, greater than H3. So my abrasive particles can remove only H3. It cannot remove H1. That means because H1 is much harder or slightly harder than H2. That is the concept of chemomechanical polishing process. Here in this particular thing, CO2 is used for the silicon carbide and achieved a greater surface finish. This is the initial surface finish on which the chemical is applied or chemical blended magnetorealistic fluid is used, and after using polishing with 800 mesh size and then 400 oil based mesh size and other things. When you use the water based, as I said, two varieties of fluids are there. One is water based and one is oil based. Oil has not much affinity towards the silicon surfaces, so water has a much better affinity. So it is making a passive layer on the surface. You can see here how the surface finish is achieved. 0.01, that is 1 nanometer surface finish is achieved using this one. You can clearly see how the best surface is achieved on a silicon surface. Okay, so you can see here how the optical views of finished surfaces where IIT Kanpur, BARC, DST particular project which we have done at IIT Kanpur under Professor V.K. Jain's laboratory, all these things. This is about the magnetic field intensity based finishing processes as such. Okay. So what are the accomplishments and other things that we have done? So applications and achievements that we have done used at laboratories. So evolution of abrasive flow finishing from abrasive flow machining process. It is Rome, as you know, Rome is not built today. So at the laboratory in 1960s, 1996 and 97, first version of abrasive flow finishing is developed at IIT Kanpur. Then when we worked on this one, we developed another abrasive flow finishing process. Then we moved to a flexible rotational abrasive flow finishing process in 2005-06. Then high speed rotational abrasive flow finishing process is developed 7-8, and we have developed a approximately smart based flexible abrasive flow finishing in 2019 and 20. So this is, yeah, as I said, no, Rome is not built in a day. So lot of evolution taken place. Initial stages when Professor Gorana used to work on this setup, people you require, if at all I want to do one experiment in 1996 and 97 setup, you require another 2 people to lift the plates and other things. As we progress now, no human much effort is required on a smart machine. That is how we have transformed from 1 to 2. So that's what I said, smart, we achieved capabilities, paper to product technologies. We have designed and developed a approximately smart one, but it is not fully smart because it has few sensors and we need to upgrade with another sensors and cloud computing systems and where the data can be monitored and other things are going on. As he said, the achievements, we have developed one system along with our patent at the CMTI. It's a AFM 150D. 150D stands for diameters, where the finishing has done on many advanced workpieces ranging from biomedical to aviation to defense and other things. We have patented this technology of abrasive flow finishing process, where abrasive flow finishing setup is patented, abrasive flow finishing medium is patented, and we have patented multiple mediums, and we are commercially, we are not in a position to sell, but we are serving many industries in terms of finishing. Regarding other things, if the students are there, you can go through some of the NPTEL courses which I developed. If at all you want to know more details about whatever I taught, see what this 1 hour or 1.5 hours, I can teach only some basic things. If at all you want to know sustainable machining and many other things, you can go through the course Introduction to Machining and Machining Fluids, which is freely available on YouTube. You can just type Introduction to Machining and Machining Fluids by Dr. Ravi Shankar, so you can get it. Another one course is Introduction to Abrasive Machining and Finishing Process. What all the processes that you are seeing in this one, so you can get these things in this particular course. So where you can start with abrasive machining process like abrasive jet machining, abrasive water jet machining, and ultrasonic machining. This also will be there along with the conventional machining like grinding, lapping, honing, and other things. At the same time, you also go to the advanced finishing processes such as abrasive flow finishing, magnetobiological finishing, and CMPs and other things. So we have another third course which is precisely for the PG students. So that is on polymer assisted abrasive finishing process, where the polymer networks plays a major role in controlling the forces and other things. Okay, these are the courses that are regularly floated by IIT Madras NPTEL under MOOCs, massive online courses, and people can register. And those people who are working studying in third year and want to get the summer internship, so for them, this is a golden opportunity. Whenever these courses are floated, if you can top, or if you are in the top 5 people of this particular exam that is conducted by IIT Madras or IIT Guwahati or IIT Tirupati, whoever the thing. So you will get a privilege to work under me for summer internship, and this particular NPTEL division also pays you some of the stipend also. That is the motive of putting this particular slide. So what I mean to say is, if you are the topper of this particular course, and there is a heavy chance that NPTEL section will fund you for your summer internship. Okay. So as I said, I am also editorial board member for IMECI Micro Manufacturing Journal. So interested faculties who are working on micro machining and nano finishing or micro manufacturing or nano manufacturing can be submitted to the journal. So we are looking for very good quality journals to enhance the quality of the journal. At the same time, also the guest editor for 2019 and 20 for International Journal of Precision Technology. So we are also looking forward for a good and high quality materials are where the science is most important rather than changing the workpiece material or changing this. We may not, I cannot say that we are going to consider that. But what I mean to say is that if there is a good change in physics or a new physics is there, we always encourage you to submit and help us to take to a different spectrum of our journals. Acknowledgement, as the first and foremost acknowledgement that normally we do is funding agencies. We are very thankful for the funding agencies. I started my career at IIT Guwahati in 2012 March. So startup grant of 5 lakhs rupees. Then Baba Atomic Research Center. I'm very thankful to the scientists at Baba Atomic Research Center keeping trust on me at the initial stages and funding me about 23 lakhs rupees for nuclear applications. Then we got a TSDP project under DST, which is about nearly 1 crore, approximately 96.7 or something. So then we got a project from DRDO about 75 lakhs. Then a big project comes to us, that is a 60 crores project where multiple people are involved on theranostics, therapy plus diagnostics, which is biomanufacturing based or biomechanical based particular projects where we have done a extensive work on biomechanical engineering. And we have 2 imprint projects ongoing and some are under consideration. So one is with IIT Kanpur, another one is with IISc Bangalore of 6 crores rupees. So IIT Tirupati, we have around 22.5 to 25 lakhs funding is there for a seed grant, that is startup grant. And we received SERB grant for 45 few lakhs rupees, and BIRAC, as I said, we got on our extensive work on also on biomanufacturing, so coatings and other things. So we got one project from BIRAC, that is Biotechnology Industry Research Assistance, which is about 40 lakhs rupees. This is the current funding and what we have received. Some of the funding approved, but yet to receive. Those things, by God grace, things work well, and we receive in due course of time. So acknowledgement goes to the research group also, because this is a research group which is on the background works. I am just a front face, like a lab view front face, and background will be there. So just I am a guy. Here, the contribution is enormous from PhD students to the summer interns. As I said, no. So PhD students, MTech students, MS students, by MS by research students, BTech students, and summer interns. I was always fascinated about with some of the summer interns, how intensely they work for 2 months, and they also publish in highly reputed journals under me. If I just want to, because some of maybe students, that's why I'm saying some of the students who worked under me has helped the PhD students and master students and got the co-authorship in Journal of Cleaner Production, which is impact factor is around 6 to 7, JMPT Journal of Material Processing Technology, and many top-notch journals. So I always encourage sincerely hardworking and very good polite students always are welcome to our research group, and you are most welcome. So thank you one and all for your kind attention and patience also. If you have any doubts or clarifications, queries, I am most welcome for those things. And if at all you want to approach me regarding anything like JRF, Junior Research Fellow, Postdoctoral Fellow, or any other things, we have some vacancies. And as I said, we are looking for sincere, hardworking, and other things. These are all the things whenever we enter into our Professor V.K. Jain's room, we see that sincerity, hard work cannot be replaced by any other things. Okay, so we learned from things. I am also thankful for Professor Ram Kumar, Professor V.K. Jain, Professor S.K. Chaudhary, who are our supervisors at IIT Kanpur, and many mentors who come across, all the teachers who helped me in growing and other things. Thank you.
Thank you so much, sir. Thanks a lot for being with us during this session, and I hope that our participant will definitely be benefited by the your talk, sir. Thanks a lot. Now I would like to request our participant to ask some queries if they have any, or either they can write their query in the chat box so we can read them.
So where is the chat box?
Okay.
Is this? So should I start presenting to see the chart, or what is the?
Dr. Dev?
I think, sir, no query now. I'm waiting for the query because here till now nobody has responded. That's why I'm waiting for that.
Okay.
So I request everyone
Two to three, no? Otherwise.
everybody saying thank you and saying informative.
I think, sir, there is no query, I think, by the participants. So I think we can stop over here. Dr. Narendra?
Yeah, yes, sir. Yeah, no query.
So if there is no question,
Okay.
Yeah. One query is enough. One query we have.
Yeah, please.
How to engage these technologies in industrial production?
How to engage these technologies in production?
Prashant Trivedi is asking how to engage these technologies in industrial production.
Dr. Vikrant ji. So these are the technologies already there in some of the technologies are see what I said, no, we develop at laboratory scale. See, there is a TRL level, technology readiness level, TRL. So Laboratory scale, the basic research we develop is from 1 to 6. Later, what we do is we collaborate with the research laboratories and we transform this TRL level from 5 to 6 to 7 to 8 or something. Then we make sure the repeatability of this particular process, because development is one and checking the industry level readiness level is a different spectrum where people don't get publications. That is where the biggest drawback is lying, because we are not going to get publications, but enormous work will go in repeating for the repeated same precision output. Okay, so there we take the help. For example, our technology, we have patented it and we taken this to TRL level 6 and then we have given to CMTI and we collaboratively work, as you might have seen in the slides, which we have taken to TRL level 9 or 10, which is a commercial readily available machine. Now people can purchase this machine. That is the thing. So that is, there is a standard protocols, or there is a thing like some of the companies, whenever we develop these technologies, will approach for 5 years royalty. So like that also the people will take. So otherwise, some of the technologies are not so stringent or difficult to develop. So some of the things they will develop, like some of the machines like MAF or laboratory skills that I have shown, that can be easily developed by you people at your laboratory also. Only thing is that you need to rigorously go through these things and you have to understand what is the concept, what is the science and physics behind it, and you have to make sure that only thing is that you have to have version 1, version 2, version 3, like upgradation you have to do. So then, as I said, no evolution. So it will take few years. I cannot say if you are constantly working on that, you can develop in 1 year itself.
Sir,
Tell me, sir.
sir, another question we have from Nilesh Kumar Bhoi.
Yes, sir.
How did different phases in composites affect the nano finishing process, especially for the lightweight composite materials?
How different phases in composite affect the nanofilms? So as I understand the question says, assume that I have a metal matrix, it's a lightweight composite materials, okay. So you are talking about metal matrix composites or polymer composites? That was, I don't know, assume that metal matrix composites, okay. So
Yes, sir.
metal composites, you have two phases, one is a reinforcement phase, another one is a matrix phase. In lightweight, normally you go ahead with aluminum alloy and silicon carbide. So if at all, if you want to understand this particular physics, there is one paper by myself, Dr. Ravi Shankar and Professor V.K. Jain in 2009 by Wear Journal. Okay. So here is a shear strength of the material has to be understood, and there is a chemically interacted or elementally interacted regions are there at the reinforcement surface. These are clearly explained in the paper that is published in 2009 Wear Journal, WEAR Journal. So you can go through that journal. So if the reinforcement is above the mean line, what will happen? If the reinforcement is below the mean line, what happens? If so, and other things. Whenever it is abrasive particle is touching the reinforcement, what is the physics? Whenever the abrasive particle touches the matrix, what is the physics? Everything is clearly explained in that particular journal. So, because it will take a lot of time to explain.
Sir, another question is how useful this technology in human implants and other prosthetics?
Yeah, this particular technology is very much useful in human implants, basically. Prosthetics. So if your prosthetics means external means, so prosthetics normally will be made up of polymers. So this may not be very good for polymers, but implants, as I said, ceramic implant or metal implant or alloys implant, this is much useful. Obviously, as you have seen clearly in the slides. So if you have doubt, you can always, please sir.
Another is running again from Vikram Trivedi, and he says where the tribology is main concern.
So if you take the tribological aspects, for example, knee implant, what you have seen. So knee implant undergoes a relative motion. Okay, so there you require a super finishing. If your super finishing is there, or a nano polishing or atomic scale polishing is there, the load bearing area will be more. If you are not going to polish, what will happen? The load will be on the peaks. Assume that your surface is a triangular surface. So the load will be on the top of a triangle where the area is very less. So there will be a deformation or shearing. Both will be there because of the relative motion and because of this eccentricity problems will come. So wherever there is a relative motion, for example, if you take a hip implant, in a hip implant, normally acetabular socket and acetabular head are finished properly. Inside of acetabular socket and out the surface of an acetabular head only polished. Rest all the things you require high rough coatings or highly rough texturings. Okay, because acetabular socket and acetabular head you require super polishing because you need a relative motion there. Because if you do twist your wrist, so your acetabular socket and acetabular head is most important. So if you want further details, you can mail me. So don't be hesitant because the relation between you and me should not end at this point of time. If I can help you, I definitely help you. If I cannot help you, I say frankly that, sir, I cannot help you like that. Okay. Don't feel that, oh, they are IIT faculty and no, we are humans. Okay. So treat us like that and you can always have a relation, collaboration and other things. Okay.
So another question is that this technology is good for MEMS and other nano electronic devices?
Yes, sir. So this technology is very good for MEMS, in particularly microfluidic based MEMS. So one of the papers which we have or our researcher collaborators have done is microfluidic channels can be polished by this particular technologies, so that you can control the flow of serum, you can control the flow of body fluids, you can control, because otherwise no, if you just do the micro machining and leave, there will be a lot of backflow because of the rough surfaces at the walls. So you need to polish. When there is a requirement of mixing and other things or proper flowing of the chemicals, see, whenever MEMS mostly used for diagnosing applications. Assume that one of the examples that I have shown using micro machining using bioorganisms, there micro mixture is there, micro nozzle is there. There you need a precise flow and controlled flow. So at the same time your surface also should be away from metallurgically destroyed layers such as recast layer and other things. That's why polishing is most important on a micro machined surfaces.
Sir, can we make TAM samples by using this technique, unlike FIB? The participant has the brittle intermetallic samples.
Sir, Vikrant Trivedi ji, I have not talked about FIB. Focused ion beam machining, I have not talked. So this is not pertaining to that particular area. So you can write to me, or so you can write to the right people, because I never worked on FIB. So I may not be the right person to answer this particular question. Sorry.
Yes.
But maybe Yeah, see, your question has some ambiguity also because can we make 10 samples using FIB? So there is so TEM samples means I understand transmission electron microscopy samples. Whenever you are talking about transmission electron microscopy samples, the sample will be too thin. That much I can understand. So you can do because that particular process, whenever you have a TEM, there is one process called focused ion beam milling. Okay, FIM. So those things one has to purchase, and you can do focused ion beam milling process, and you can bring down to up to certain thickness. Then later on you have to go by your hand based or finger based polishing, because I have a practical experience of making a sample for approximately 3 months. One sample I want to make on a aluminum silicon carbide MMC. At the interface, I want to understand how the things are happening. For that purpose, I have made a 10 samples. So initially, you will lose lot of time, obviously. So my answer for this one, based on my experience, not based on this particular presentation, is you can do it. 10 samples you can do by focused ion beam milling, but followed by your hand-based super polishing is required, because FIB has their own limitation up to that one, and you may have a metallurgical changes on the surface. So those layers you need to remove by mechanical polishing. So what you have to do is you have to take this particular sample on your इंडेक्स फिंगर वट एवर दिखाते हैं ना, वो जो फिंगर के ऊपर वो टिप के ऊपर लेके आपको वेलवेट क्लॉथ के ऊपर डायमंड पॉलिशिंग स्लरी लेके आपको दिन भर बैठना पड़ेगा, कम से कम 7 दिन बैठना पड़ेगा, एक दिन नहीं 7 दिन बैठेगा, उसके बाद आएगा आपका सैंपल, यदि नसीब अच्छा होगा तो। मेरा नसीब खराब था तो मेरा सैंपल 3 महीने के बाद बन गया। So that is what my practical example when I am telling about 2010. Nowadays you might have sophisticated technologies.
Sir, another question is by Vikrant. He has iron mill, but samples are breaking.
That's what I said. No, you need to have optimized conditions. Okay, so these are, as I said, no. That's why. So this sample making is 1 week work only. If you say, but why I took 3 months? This is because of this one only. So that's what I said. No, you have to sit. You should have patience. Otherwise, temp sample is like वो सपना ही रह जाएगा ऐसे ही. So with nano machining we can do it or not? No, you cannot do by nano machining process. Only the machining process that you can do, as per my understanding, is iron beam milling. Then followed by hand lapping. So you take a velvet cloth, you take on a finger tip and you do it. If it is a homogeneous material, for example, it is a pure aluminum, there is no problem. If it is metal matrix composite at interface, then the problem will come. It is an different phase materials, then is a problem. There is a breakage will take place. If it is a heterogeneous material, then the problem will come. Normally, homogeneous material you don't get. But if you are a mechanical guy, first and foremost sample, you have to get help from metallurgist, and exclusively those people who work on TEM. In IIT Guwahati, in IIT Kanpur, Professor Gautama works in this area. So I spent a lot of time with Dr. Bhagya and other people. So if you are nearby IIT Kanpur, I can give one name. So I don't know whether you are nearby IIT Kanpur or not. Just you can just go to a particular laboratory. There is a TEM lab is there in IIT Kanpur. Normally, I don't know who is in charge now. When I was a student, Professor Gautama was and as for my understanding, there is one staff who was a PhD student and my contemporary. Currently, he is working as a technical officer there. His name is Bhagya. So you can take his help and you can make your samples. If you want, you can write a mail to me and I can directly connect you to Bhagya. He is my friend. That much only I can do. It's a non-technical work. Okay, I am a metallurgy student doing PhD at IIT Madras. Okay. So if you are a metallurgy student at PhD at IIT Madras, I think you should get from your seniors. So in that case, you can get from your seniors, Trivedi ji. So normally we learn from our seniors only. So it is not that we do directly. So I don't know whether how far my suggestions are helpful to you. So if at all you want, I can connect you to IIT Kanpur. If you can go and get the help, not in this pandemic. After the situation is fine.
Okay, sir, I think those were very good. Hello, sir, I think no more query. So thank you, sir, for sharing your experiences with the participants. And thank you, sir, for your time.
Yeah, so thank you giving me the opportunity, and so especially see personally I never met Dr. Ravi Pratap Singh, but I am very thankful to you. So you have,
Thank you, sir.
or maybe you might have seen my web page and other things, and you might have thought that I am one of the who work
Yes,
in.
sir. I gone through your profile and I found very suitable for this particular thesis, so I just sent an invitation and thanks for your acceptance.
Yeah, thank you. So
Okay, sir.
convey
Thanks
my
a lot.
people. So okay. Thank you. Can I disconnect?
Yes, sir, yes, sir.
Thank you, audience, one and all. And if you need any help from my side, you are always welcome to write a mail. So with a clear-cut query. Don't
Thank you, sir.
write in a vague way. So please write in a clear-cut way, and the maximum extent I try to help you. If I don't know the answer, at least I can connect to the right people at least. That much I can do. Okay. Thank you, one and all, and hope to meet you sometime in some conferences.
Thank you. Thank you.
Thank you.
Thank you so much.
Yeah, please.